Good evening, friends. Welcome to day 4 of the Six Sigma Masterclass Elite sessions. So, we had just stepped into the second phase in the DIVIC approach, which is the measure phase. So, we started with understanding what is data. Data is numerical expression of any activity. So, without data, there can be any number of perceptions or opinions about a process performance. But with data, there can be only one conclusion. But then the data has to be unbiased. So if you're dealing with biased data, it would lead to ego situation, garbage in, garbage out kind of a situation. And we also looked at what are the various elements that would be part of the data collection plan. So this data collection plan, as I told you last Friday, will serve as an approval document for the process team lead to hand over necessary data to the project team representative because data is supposed to be a confidential information. So it cannot be just like that handed over to anyone, right? So that being the case, the process team lead would require a proper authorization or approval from the leadership to hand over the data pertaining to that process to the project team representative. So this data collection plan would serve as the approval document for the same. So the data collection plan would consist of the CTQ metric along with the operational definition. So we also discussed about the operational definition, which is nothing but the calculation logic that we would adopt for calculating that CTQ metric. And then we will also identify the baseline period for which the base data for the CTQ metric needs to be collated. And I had clearly informed that the baseline period should be the latest 1 year period. For any Six Sigma project exercise, the baseline period that we need to consider is the latest 1 year period because if the process performance has a lot of fluctuations and if you are considering the 1 year period performance, then in that case, it will average out. Otherwise, if you are considering a quarterly period as the baseline period, then that quarterly period could be favorable to the process or it could be not so favorable to the process, and that may not reflect the true performance of the process as such. So it's always better to consider the latest 1 year as the baseline period. The third pointer, we need to identify the time frame during which the project team representative will visit the process team and collect the base data. And then the fourth one is identify the project team representative who would be collecting the data. So the employee ID of the project team representative would be clearly displayed as part of the data collection plan. And then the fifth pointer, we need to identify the source of data collection, whether the data would be compiled from Excel reports or it would be pulled out as a report from the workflow tool. And then the final one, we also need to identify the graphical format that will be used for projecting the CTQ metric performance, right? So these are the various things that would form part of the data collection plan. So let us continue with the discussions about the data concepts. Next, we are going to look at the types of data. Let me just share my screen. So this is very, very important. So the data types, because we need to identify the correct data type at the beginning of the project exercise, because we do have specific set of statistical tools and techniques applicable for each of these data types. That being the case, so we need to identify the correct data type in order to use the relevant statistical tools and techniques to analyze the same. Otherwise, what will happen? If you are going to identify the data type incorrectly, then we will end up applying some incorrect statistical tools and techniques, and that would obviously lead us into that GIGO situation, garbage in, garbage out kind of a situation. So let me just put today's date, right? So we are now going to look at a very important section in the measure phase, which is types of data. So data, as we can see, is broadly classified into two types. One is called the discrete data, and the other one is called the continuous data. So data, as we can see, is broadly classified into two types. One is called the discrete data and the other one is called the continuous data. So what is a discrete data? So discrete data is nothing but the count data which can be expressed only in terms of whole numbers. So discrete data is a count data which can be expressed only in terms of whole numbers. So what do you mean by whole number in mathematics? Any number or any value without decimals will be called as a whole number. Say for example 1 or 2 or 3 or 4 or 5 or 356, 458. So any value without decimals will be called as whole numbers. And this discrete data cannot be expressed in decimals or fractions. In fact, it will not make any sense if you are going to express this discrete data in terms of decimals or fractions, right? So, for example, number of participants in a training session. So we can either say that there were some 26 participants or 15 participants or 10 participants or 13 participants, etc. So it will not make any sense if I'm going to say that there were 13.25 participants who attended the training session, right? So this metric can be expressed only in terms of whole number. Similarly, number of units processed. So I can say that we processed 250 units today or 254 units today or 265 units today. So it will not make any sense if I'm going to say that we processed 250.82 units today, right? So again, number of units processed can be expressed only in terms of whole numbers. It cannot be expressed in decimals or fractions. Similarly, number of defects. So I can say that we identified something like 20 defects today, or 23 defects today, or 32 defects today. So it will not make any sense if I'm going to say that we identified 30.5 defects today. Again, number of defects, as we can see, can be expressed only in terms of whole number. It cannot be expressed in terms of decimals or fractions. So all these matrices that I have quoted as examples for discrete data, as we can see, these matrices can be expressed only in terms of whole numbers. They cannot be expressed in terms of decimals or fractions. Whereas continuous data is a measured data which can be expressed in decimals or fractions apart from whole numbers, right? So continuous data is a measured data which can be expressed in decimals or fractions apart from whole numbers. Say for example, length of a product. So the length of a product can be 10.2 centimeters or it can be exactly 10 centimeters, right? So all these matrices that I have quoted as examples for continuous data, if you look at, they can be expressed in terms of decimals. It would make absolute sense if you are going to express these matrices in terms of decimals. And these matrices can also be expressed as a whole number. Again, weight of a product. I can say that this product weight is 2.5 kgs or it can be exactly 2 kgs. Time taken to produce. So time taken to produce a unit item is 15.25 minutes or it could be exactly 15 minutes. So cost of a product. So this product cost is $1.75 or exactly $1, right? So all these matrices that I have actually quoted as examples for continuous data, as I told you, can be expressed in decimals or fractions apart from whole numbers. So it would make absolute sense if I'm going to express all these matrices in terms of decimals or fractions. So this is the key difference between the discrete data and continuous data. So while discrete data cannot be expressed in decimals or fractions, it can be expressed only in terms of whole numbers. Continuous data can be expressed in decimals or fractions apart from whole numbers. But then let me provide you with a very simple clue for you to identify whether a particular data is a discrete or continuous, right? So we need to look at the unit of measure. So if the unit of measure cannot be broken into different levels, then it would be classified as discrete data. On the other hand, if the unit of measure can be broken into different levels, then it will be classified as continuous data. So if you look at discrete data, number of participants, what is the unit of measure here? Number. Can it be broken into different levels? No. So hence it will be discrete. Whereas if you look at length of a product, what could be the unit of measure? It could be expressed in terms of centimeters. So centimeters as a unit of measure can be broken into different levels. So it can be broken into meters, millimeters, etc. Similarly, weight of a product, it will be expressed in kilograms. Kilograms can be broken into different levels, grams, milligrams, etc. Time taken to produce, it could be expressed in terms of, say, minutes or even hours, hours, minutes, seconds, etc. Cost of a product could be in terms of dollars. So dollars can be broken into cents. So if you look at the unit of measure for all these matrices that are provided as examples for continuous data, they can be broken into different levels. So that is why it is called as continuous data, whereas the unit of measure for the matrices I have provided as examples for discrete data cannot be broken into different levels, and that is why these matrices are classified as discrete data matrices. So this is the broader classification. So if you are going to count a few units and then express it as a whole number, it will be discrete. Or if you are going to measure a dimension of a product and express that value in decimals, then it will become continuous, as simple as that, right? But then under discrete, we have a subclassification. So we have what is called binary discrete data. So under discrete data, we have binary discrete data as a subclassification. So as the name itself suggests, so what is binary? Binary means there will be only two options for a result, right? So that is when we would call something as a binary. So there will be only two options for a result. Say for example, if you toss a coin, right? So what are the two options for a result? We can either get a head or a tail, right? Similarly, if a student sits for an exam, the student can either pass in the exam or fail in that exam. Or if you are going to inspect a sample unit, the sample unit can either be defective or non-defective, right? So all these things, pass or fail, defective, non-defective, heads or tails, go, no go, all these are binary data. So wherein we will have only two options for a result. But then if you have a third option for a result, it will not be called as a binary. It will be called as a tertiary, right? We all know that. So binary means there will be only two options for a result. Then only it will be called as a binary, right? But then we can clearly understand when we express this binary data, it cannot be expressed merely as a whole number, right? Say for example, we are talking about the number of students who are passed in the examination pertaining to a particular classroom. So if I'm going to say that 75 students have passed in the examination, right, with regard to a particular classroom, does this actually give the complete information about the performance of that class? Definitely not. It gives only a partial information. I can get to know that 75 students in this classroom have passed in the exam. That's it, right? So it doesn't really provide me with the complete information about the performance of the classroom. So what I would ask immediately if someone is going to say that 75 students in this classroom passed in the examination, the next question I will ask is out of how many, right? So that is the obvious question that I will ask. So when we say that 75 students have passed in the examination, the next obvious question will be out of how many. So we need to have the denominator in place. So it can be 75 out of 75. 75 out of 75 means 100% pass. That is an excellent performance. 75 out of 100 means 75% pass. 75 out of 150 means 50% pass. So 75 students passed in the examination, as we can see, doesn't give the complete information with regard to the performance of that classroom. So when I express this in terms of a proportion value or a percentage value, I would be able to get the complete information with regard to the performance of that classroom. So 75 out of 100, when I say 75% or 0.75, which is the proportion value, then I can understand, okay, 75% of the students have passed in the exam. So merely quoting this as a discrete value will not give the complete information about the performance of the classroom. If I'm going to say that 75 students passed in the exam, it does provide me with some information, but doesn't give me the complete information with regard to the performance of the classroom. As I told you, it could be 75 out of 75 or 75 out of 100 or 75 out of 150. So depending on the value of the denominator, I can understand what is the performance of that classroom, right? So whenever we express this binary data, it will be expressed in terms of proportion, right? So when I express this in terms of proportion, say 75 out of 100 means what is the proportion value? It is 0.75. So this proportion value, if it is multiplied by 100, will give me the percentage value. So 0.75 multiplied by 100 will give me 75%, right? So that is how we would convert a proportion value in terms of a percentage value, or we can even do it in the reverse direction. A percentage value can also be converted in terms of a proportion value. Say 5% will be written as 0.05. 10% will be written as 0.1. 20% will be written as 0.2. 2% will be written as 0.02. So we should be comfortable converting a decimal proportion value in terms of percentage value. Similarly, percentage value in terms of the decimal proportion value, right? Similarly, if I'm going to say that we identified something like 10 defectives, right, today, it doesn't give the complete information about the performance of the process. The next obvious question will be 10 out of how many? Is it 10 out of 50? Is it 10 out of 100 units inspected? Or is it 10 out of 200 units inspected? Right? So, depending on the denominator value, we will be able to understand the performance of the process. So, when I say 10 out of 100, it means 0.1 or 10% is the proportion of defectives, right? So, proportion is the appropriate metric that would be assigned to expressing the binary discrete data, right? Proportion is the metric that would be assigned to expressing a binary discrete data. So if you are going to express this binary discrete data in terms of whole number, we can understand that it doesn't give the complete information. So we obviously need to express this in terms of proportion. But then proportion value, as we can see, will always be expressed in terms of decimals, right? So if you say 2%, it is 0.02 in terms of proportion. If you say 10%, it is 0.1. If you say 75%, it is 0.75. So if you look at the proportion value, it will always be expressed in terms of decimals. Just because the proportion value is expressed in terms of decimals, we cannot straight away classify it as a continuous data. So we need to be careful here. So we need to understand that proportion is a derived value, not a raw value. So the broader classification that we saw, wherein we classified the data types as discrete data and continuous data, we dealt only with the raw data. We just counted the number of participants and expressed that as a whole number, or we measured the length of a product and expressed the measurement value in terms of decimals. That's it. We didn't apply any formula there. But when we are calculating the proportion value, right, we would be using a formula containing a numerator and a denominator. So whenever we use a formula, the resultant value can very well be expressed in terms of decimals. Just because the resultant proportion value is expressed in terms of decimals, we cannot straight away classify it as a continuous data. We need to understand that proportion is a derived value. Derived means it is derived applying a formula containing a numerator and denominator. So it can be expressed in terms of decimals. So we need to understand that, right? So when proportion value is expressed as decimals, we need to look at whether the metric, the formula for the metric for which we have derived this proportion value fulfills the three conditions or not. Then only the proportion value will be treated as binary discrete data. So whatever the proportion value that we would get, even though it is expressed in terms of decimals, we need to look at whether the metric or the formula that we used for calculating that metric proportion value fulfills the following three conditions. then only that proportion value will be called as binary discrete data, and the metric would be termed as binary discrete metric. Clear? So what are the three conditions? Both numerator and denominator should be count discrete. So discrete, count discrete all mean one and the same. So both numerator and denominator should be discrete values. That is the first condition. The second condition, numerator should be a subset of the denominator. When I say subset of the denominator, it means the numerator should be a part of the denominator. So whatever value we have as the denominator, the numerator count should be a part of it, right? So that is the second condition. Numerator should be a subset of the denominator. And there should be only two options for a result. Then only it will be called as a binary data, right? So this is an obvious condition. There should be only two options for a result. So if the formula that we have used for deriving this proportion value fulfills all these three conditions, as I told you, the proportion value will be treated as binary discrete data, and the metric for which the formula was applied will be considered as binary discrete metric. Again, if you are going to toss a coin, right? So if you are tossing a coin for 100 times and you got heads 80 times. So if you are going to merely say that you got heads 80 times, it doesn't give the complete information, right? But when you say that I got heads 80 out of 100 times, that means 80% is the percentage or the proportion of heads, right? And 20% is the proportion of tails. So when it is a binary discrete value, then it's very easy for us to understand what would be the proportion value for the other option. So once I say that 80% is the proportion of head or percentage of heads, then it automatically means that 20% will be the proportion of tails, right? Similarly, when I say 0.75 or 75% is the pass percentage, it would automatically mean that 0.25 or 25% is the fail percentage, right? So when we actually derive proportion of a particular option, we can easily understand what will be the proportion of the other option. So when I say 10% is the defective proportion, it would automatically mean that 90% is the accurate proportion or non-defective proportion. Now let us look at a couple of examples and see
Hi, sir.
whether, yeah.
Would you be able to explain the first point again? Both numerator and denominator should be
Yeah, we
counted.
are coming there. Now I will explain through an example. So we
Okay.
are looking at the matrices and see, whether these three conditions, apply for the formula that we are going to have for that metric. So how will we calculate the pass proportion? So what will be the numerator and what will be the denominator? So pass proportion can be calculated by applying the formula. Number of students who are passed in the exam divided by the total number of students who appeared for the exam. So here what is the numerator? Number of students who are passed in the exam is the numerator. And what is the denominator? Total number of students who appeared for the exam. So when I say 75 out of 100, it means 75 is the number of students who are passed in the exam. And 100 is the total number of students who appeared for the exam, right? So 75 is the numerator, 100 is the denominator. Now let us look at whether this particular formula that we have for pass proportion fulfills the three conditions or not. What is the first condition? Both numerator and denominator should be count discrete. So number of students who are passed in the exam. Can this be expressed in terms of decimals? Will it make any sense? No, this can be expressed only in terms of whole number, right? I can say either 78 students passed in the exam, or 73 students passed in the exam, or 76 students passed in the exam. It will not make any sense if I'm going to say 75.53 students passed in the exam, right? So number of students who are passed in the exam can be expressed only as a whole number, and hence this is discrete data. Similarly, if you look at the denominator, so what do we have in the denominator? Total number of students who appeared for the exam. So again, this particular value, can it be expressed in decimals or fractions? Will it make any sense? Definitely not, right? So I can say either 100 students appeared for the exam, or 110 students appeared for the exam, or 105 students appeared for the exam. So it will not make any sense if I'm going to say 102.65 students appeared for the exam, right? So again, total number of students who appeared for the exam can be expressed only as a whole number. So that is also a discrete value. So both numerator and denominator are count discrete. So the first condition is fulfilled. Understood? The first condition, both numerator and denominator should be count discrete, right? And the second condition, numerator should be a subset of the denominator. So as I told you, the numerator count should be part of the denominator count. So what is the denominator count? Total number of students who appeared for the exam. So this denominator count, which is total number of students who appeared for the exam, we will have the count of number of students who are passed in the exam, as well as the count of number of students who have failed in the exam, right? So then only you'll get the total number of students who appeared for the exam, correct? Now we can see that number of students who are passed in the exam will be included in the count of the total number of students who appeared for the exam. So here is the case where the numerator is indeed a subset of the denominator. Clear? And there should be only two options for a result. So here we are talking about the student appearing for an exam. So when a student appears for an exam, so what are the two options for a result? The student can either pass in that exam or can fail in that exam. So only two options for a result, and hence pass proportion, even though it is expressed in terms of decimals, will qualify as binary discrete metric, and the proportion value will be considered as binary discrete data, right? So why I'm explaining so much? Because we do have specific set of statistical tools and techniques applicable for binary discrete data. So if you're not going to identify the data type correctly, then we will end up using some irrelevant statistical tools and techniques, and we will also get some incorrect results. And that would lead us into the ego situation, garbage in, garbage out kind of a situation. So if you are having a proportion value, right? If something is expressed in decimals, first find out whether it is a raw value or a proportion value or a derived value. So if it is a derived value, just look at the formula which was used for deriving that value. If that formula fulfills these three conditions, then the derived proportion value, even though it is in terms of decimals, will be classified as binary discrete data. But then, if that formula doesn't fulfill any of the three conditions, then in that case, the resultant proportion value will not be considered as binary discrete data. Clear? Now let us look at the second example. So accuracy proportion is a very famous metric, right? So how will you calculate the accuracy proportion or the accuracy percentage? So you should be knowing the formula, right? So the formula is number of non-defective units or number of accurate units in the numerator divided by the total number of units inspected, right? So number of non-defective units or accurate units divided by total number of units inspected. So if you multiply this by 100, you'll get the accuracy percentage. Or if you're going to leave it as it is, you will get a decimal proportion value, right? So let us see whether this formula fulfills all these three conditions or not. So what is the first condition? Both numerator and denominator should be count discrete. Number of non-defective units. Can it be expressed in decimals? Definitely not, right? So it can be expressed only in the whole in terms of whole numbers. So this will be a discrete value. Again, total number of units inspected. Can we express this in terms of decimals? Again, we cannot express this in decimals. It can be expressed only in terms of whole number. So both numerator and denominator are count discrete or simply discrete values, right? And the second condition, numerator should be a subset of the denominator. So what is the denominator? Total number of units inspected. So the count regarding the total number of units inspected will include the count of the number of non-defective units as well as the count of the number of defective units. So the number of non-defective units will be part of the total number of units inspected. So the numerator is indeed subset of the denominator. And what is the third condition? There should be only two options for a result. So when you inspect a sample unit, what are the two options that you can get as a result? The sample unit can either be a defective sample or a non-defective sample, right? So only two options for a result, and hence accuracy proportion or accuracy percentage, even though it is expressed in terms of decimal value, it will be considered as binary discrete data. Clear? So you can have the accuracy percentage as even 99.5% or 99.73%, but still that value will be considered as binary discrete data, right? So in terms of proportion, 99.73% will be written as 0.9973, right? So you'll be rounding it off to 4 decimal places. So 0.9973, the decimal value will be treated as binary discrete data because the formula that we used for deriving this proportion value has fulfilled all these three conditions. Clear? So yet another example, turnaround time adherence to target, right? So or you can simply say time adherence to target. So customer would have given the target time within which the delivery of the output should take place. So how many units out of total number of units processed were actually delivered within the target time specified by the customer, right? So that is the metric that we are going to calculate here. So turnaround time adherence to target, the formula will be number of units processed within the customer target time. Say for example, the customer has given 3 days as the target time for delivery. So we will be looking at how many units were delivered or how many units got processed within that customer target time of 3 days. So that will be the numerator divided by the total number of units processed. So out of the total number of units processed, how many units got processed within the customer target time is what we are trying to solve here, calculate here, correct? So number of units processed within the customer target time can be expressed only in terms of whole numbers. So I can say we processed say 250 units or 253 units or 251 units. So it won't make any sense if I'm going to say that we process 250.62 units within the customer target time, right? So the number of units processed within the customer target time can be considered as a discrete value. So it will be a count discrete data. So the total number of units processed again can be expressed only in terms of a whole number. It cannot be expressed in decimals or fractions. So total number of units processed, which is the denominator, can also be expressed as a discrete value. So both numerator and denominator in this formula are count discrete data. And the numerator should be a subset of the denominator. So total number of units processed, the count will contain the number of units processed within the customer target time, as well as the number of units processed outside the customer target time. So you might have taken more than 3 days to process certain number of items. So when I say total number of items processed, so it would include the count of the number of units processed within the customer target time, as well as the count of the number of units processed outside the customer target time. So the numerator here is indeed is a subset of the denominator. And there should be only two options for a result. So when you look at a particular processed unit item, so it can be processed within the customer target time, or it can be processed exceeding that customer target time. So these are the two options for a result, right? So either that unit item can be processed well within the customer target time, or the unit item can be processed exceeding the customer target time. So these are the two options for a result, and hence the turnaround time adherence to customer target will be considered as binary discrete metric, and the proportion value that we would get applying this formula will be considered as binary discrete data. Clear about binary discrete data? So one thing that we need to clearly understand here is these are all derived values. So proportion is not a raw value, it is a derived value. And when we derive applying a formula, we can get the value in terms of decimals. So just because the value is in terms of decimals, please do not straight away consider it as continuous data. So we need to look at whether it is a raw value or a derived value. If it is a raw value, if it is expressed in terms of decimals, then it will be continuous data. But if it is a derived value, please spend some time in trying to understand whether the formula used for deriving that value fulfills these three conditions or not. If the formula fulfills these three conditions, then the derived proportion value will be considered as binary discrete data, and the metric for which the formula was applied will be considered as binary discrete metric. Clear? So proportion is the primary metric for us to express a binary discrete metric. Fine. And what about the count discrete? So count discrete data can be expressed in terms of average. So if you want to, calculate, or if you want to express a count discrete data set, or if you want to derive the representative value for a count discrete data set, then average is the representative value for a count discrete data set. And this average is denoted by this notation called lambda. So this is the symbol for lambda. So we need to be familiar with this. So average expressed in terms of lambda is the representative value for a count discrete data set. So let us look at a simple example here. So we have the day-wise count of number of units processed. So day 1, we have 248 units processed. Day 2, 253. Day 3, 241. Day 4, 244. Day 5, it is exactly 250. So as we can see, number of units processed can be expressed only in terms of discrete values or whole numbers, because this is a discrete data, as we all know, right? So it cannot be expressed in decimals or fractions. It will not make any sense. So number of units processed is a discrete data, and we have the discrete values for 5 days of production. And if you want to calculate average, so how will you calculate? So average can be calculated applying the manual formula. So first we need to sum all these number of units processed. So whenever we write a formula in Excel, we'll always start with equal to sign. So you can also put a plus sign. But then for easy understanding, in order to have some kind of a standardization, it's better that we put a equal to sign. So equal to sum, right? If you give the string and then open bracket, we simply need to provide the range of the values which you are going to add. So these are the values I want to add. So sum of this particular range divided by the total number of days. How many days data we have considered? 5 days of data we have considered. So divided by 5. So get the value 247. So if you want to expand this, it is actually 247.2, right? So we would be getting a decimal value. It's every possibility that we might get a decimal value when we calculate the average. So average can be calculated by summing up all the discrete values divided by the total number of data points, right? So here we get the value 247.2, and this 247.2 is a decimal value, as we can see, but then we are calculating average for a count discrete data set. And I have told you that average should be a representative value of the original data set. So what is the data type of the original data set? It is a discrete data type. So the original data set the type is discrete data, but then how come the average can be considered as a continuous data just because it is expressed in terms of decimals? So average being a representative value of the original data set will also be considered as a discrete data only. But we need to understand that average is a derived value. So it is not a raw value. It is a derived value. When I say derived value, we apply some formula to derive this average value. So whenever we apply a formula to derive a value, so the resultant value can be expressed in terms of decimals. But then we are calculating average, which will be a representative value for a count discrete data set. And if you happen to get the average in terms of decimals for a count discrete data set, what is the adjustment that we need to make? We need to round this off to the nearest whole number. That's it, right? Because average being a representative value of the count discrete data set cannot take decimal values. So even if you get decimal value as average, so what is the small adjustment that we need to make? We need to round it off to the nearest whole number, right? But then if you are calculating average for a continuous data set, so it can be done even for a continuous data set, right? So instead of number of units processed, you have the processing time data for some 5 units, right? So if you have processing time data, obviously the data would have been expressed in terms of decimals. And if you are calculating average for it, so the same logic should be applied for calculating the average. And if you happen to get the average value also in terms of decimals, we can leave it as it is because the average for a continuous data will be treated as continuous only. So even if you get decimal value as an average, we can just retain the decimal value as it is. But average for a count discrete data will be considered as count discrete only. And if you happen to get the average value in terms of decimals, what is the small adjustment we are supposed to make? We need to round it off to the nearest whole number, right? Because average for a count discrete data set cannot take decimal value, so we need to round it off to the nearest whole number. But since we apply a formula to calculate the average value, there is a possibility that you might get the average value in terms of decimals. And if you do get the average for a count discrete data set in terms of decimals, the small adjustment that we need to make is round it off to the nearest whole number. Again, when I write this average metric, it should be written in its fullest form. So we should not be merely writing this as average is equal to 247. So that will not give the complete information. People would understand that you have calculated some average value. But what is this average value? No one will be able to tell, right? Many times I've seen, when they write the average value, the metric they will quote is average is equal to 247. No one will know for what data set they have calculated the average and what is the reference characteristic that has been considered here. So the fullest form of this metric is, for this scenario, it will be written as average number of units processed per day, right? So this is the fullest form of the average metric so that we will be able to clearly understand we have calculated the average for the number of units processed and the reference characteristic is per day because average can be calculated with respect to anything. It can be calculated with reference to per day or per shift, per person, per system, right? So the reference characteristic also becomes all the more important when you write the average metric. So the fullest form here is average number of units processed per day, right? So please learn to write the metrics in its fullest form. Just do not write this merely as average is equal to 247. That will not give the complete information about that particular metric. So we need to write this as average number of units processed per day. And per day is also very, very important as I told you, right? So that is what we would call as the reference characteristic because the reference characteristic can be anything. It can be per day, it can be per person, it can be per system, it can be per shift, right? So how will we know what is the reference characteristic that we have considered for calculating this average metric? So we need to mention that reference characteristic as well as part of the metric name. Clear? So this is the fullest form of this average metric. So that is what I have summarized here. So average metric is also a derived value and is the representative value of the original data set. So just imagine a scenario where a team has won a prize, right? In an organization, a particular team, a process team has won a prize. So the entire team cannot be accommodated on the stage. So what the team will do, the team will depute its lead or the manager to go to the stage and then collect the prize on their behalf, right? So here the manager is not going as an individual. He is going as a representative of the team, right? So the manager characteristic will be deemed to be the same as that of the team. It cannot be different. The same way, when we calculate the average, which is supposed to be a representative value of the original data set, if the original data set is discrete, the average will also be considered as discrete only. But if the original data set is continuous, the average will be considered as continuous data. Clear? So average metric is also a derived value and is the representative value of the original data set. But since average is a derived value, it may appear in terms of decimals. But then if you are calculating average for a count discrete data set, the average will also be considered as count discrete value. And if it is in decimals, we need to round it off to the nearest whole number. But then if you are calculating average for a continuous data set, and if the average value is expressed in terms of decimals, we can retain the decimal value as it is because continuous data, as we all know, can take decimal values, right? So with this basic introduction about the data concepts, now it's the time for us to get started with statistics, right? So the first part of the statistics, we are going to look at the descriptive statistics measures. So this is the ABCD of statistics, right? As I promised on the very first day. So we are going to start everything right from the scratch. So we are going to start from the ABCD of statistics, and we are going to learn statistics only to the extent of what is required as part of our Six Sigma curriculum. So we are not going to go beyond that, right? I myself do not know anything beyond that. Let me make that disclaimer straight away, right? Because I am not a statistician or a mathematician. I am basically a finance person, right? So I know statistics only to the extent of what is required as part of our Six Sigma curriculum. So we will learn all these statistics in a very, very simple way, right? I will quote only simple examples. Maybe in the exercises, you may see some complex numbers, but then when we learn all these concepts, we will always learn it through some simple examples, right? So let us not complicate any of these things. Please do not over assume. Just keep it very, very simple. All these are simple concepts only, right? As long as we keep it simple, it will appear simple to us. But if you want to complicate it, then we can definitely get confused easily. So please do not overthink. Please do not get confused. Let us keep it very, very simple. So descriptive statistics, there are two
Sridhar,
categories of it. Yeah,
sorry to interrupt you.
no problem.
Uh, I just wanted to know at least one example of a continuous data. So we had a good description of the discrete data, but I could
No,
definitely
I
go
had
ahead.
given the examples here, right? We also discussed about it. All these measurement dimension metrics, length of a product, weight of a product, time taken to produce, cost of a product,
Mm-hmm,
diameter of a product. So whenever we measure something and express
mm-hmm,
it in terms of a decimal value, or we have the opportunity to express it in terms of decimal value, then it will be called as a continuous data. So if you're working in a service industry, right?
uh,
So most
mm,
of the time, we will be tracking the processing time value.
Exactly.
So processing time there will be a continuous data.
Mm-hmm.
So if you are tracking number of defects, then it will be a discrete data.
Mm-hmm.
So if you are
So,
expressing proportion of defectives, it will be binary discrete data.
okay, when we talk about MTTR, the mean time to repair, does that
Mhm.
come under continuous data?
No. It all depends. Again, mean time to repair is not a raw value, right? So it is a derived value. So what is the formula used for it? So mean time. So time is the value for which we are deriving the average value. So time is a
Mm-hmm.
continuous data.
That's right.
So the average value, the mean time to repair also will be continuous.
Okay. Okay.
Okay. So it all
Mm-hmm.
depends on what is the raw value that we are using in that formula. If the main raw value is just like how I explained here.
Yeah,
So
yeah, yeah.
here number of units processed is a discrete value. So the average will also be discrete. If it is a
Okay.
processing time data set, and if you are calculating average for it, then the average will be considered as continuous because we are calculated average for a continuous data set. So mean time means we are talking about the average time taken to repair, right? So
Yeah.
here we are talking about the time data. So time is a continuous data. So
Continuous
mean
data.
time will also be continuous,
Okay. Okay. Yeah.
right?
That clarifies. Yeah.
Yeah.
Thank you.
So there are two categories of descriptive statistics measures, measures of central tendency or location. These are also called as measures of average. And the other category is measures of variation. So first we look at measures of central tendency or location, and then we will look at the measures of variation. So under measures of central tendency or location, which is also called as average measures, we have some three metrics: mean, median, and mode. So all these things you would have learned during your school days. You're just going to
Yeah.
refresh, right? So mean, median, and mode. So let us try to understand all these three matrices through a simple example. So we are not going to look at some complex data set. I'm going to keep it very, very simple. So let me consider the data set as 1, 2, 3, 4, 5. So let us not be bothered about whether it is a discrete data set or a continuous data set. So let me just have the data set as 1, 2, 3, 4, 5. So how will you calculate mean for this data set? So mean is a simple arithmetic average. Just like how we calculated average some time back, the same logic needs to be applied for calculating the mean. So we need to sum all these data points in the data set divided by the total number of data points. How many data points are there in this data set? 5 data points divided by 5. So the mean value will be 3. Very, very easy to calculate. So it's a very simple arithmetic average. Mean is a simple arithmetic average. But then we have a value, say 50 in the data set, right? This can happen, right? This is what we would call as outlier. All these terms you need to understand: outlier or extreme value. So when can you get a value, say 50, when the other data points are 1, 2, 3, 4, 5, due to what type of variation? We already seen this, right? When all the other data points are 1, 2, 3, 4, 5, in a practical scenario, you can also get this value 50 in your data set. Due to what type of variation? What are the two types of variation that we saw last week? Yes, please. Just make an attempt. What are the two types of variation we saw last week?
Common and
Common cause variation and assignable
assigned.
cause variation, right? So I told you that common cause variation, the minor variation that you would observe in a process performance for which we will not be able to assign a reason immediately. Whereas assignable cause variation is a huge variation that you would observe in the process performance for which you will be able to assign a reason immediately. So in that example also we saw the time taken to reach the office. So it was in and around 30 minutes, right? So the minor variation in the individual data points is something that we would not be able to provide any reason immediately. So we said it is due to common cause variation. Suddenly, one fine day, the same person actually reached the office in 60.2 minutes. And that 60.2 minutes will be considered as an outlier when all the other data points are in and around 30 minutes. Suddenly we get a data point 60.2 minutes. So the 60.2 minutes will be considered as an outlier or extreme value, which can happen due to assignable cause variation or special cause variation, right? So this kind of an outlier or extreme value can occur in a practical scenario due to assignable cause variation, right? So if you are going to include this outlier value in the data set, and if you are going to calculate mean, what will be the new mean? So the earlier mean that we calculated was without the outlier value, without outlier, right? Now we are going to calculate mean with outlier. So including the outlier, let me calculate the new mean. So I need to cover this entire range, including 50 divided by, now how many data points are there including the outlier value? We have 6 data points. So divided by 6. So what will be the mean? Mean is 10.83. So it has gone up from 3 to 10.83 because of the single outlier value present in the data set. So without this outlier, the mean was only 3, and 3 can be considered as a representative value of this data set where all the data points, majority of the data points are lying between 1 and 5, correct? But 10.83 cannot be considered as a representative value of the data set where majority of the data points are lying between 1 and 5. Right? If it is between 1 and 5, can consider that as a representative value because majority of the data points are lying between 1 and 5. But then because of this outlier value, the mean has gone up to 10.83, and 10.83 as a value cannot be considered as a representative value of this data set where majority of the data points are lying between 1 and 5. But then when we talk about average metrics, it is supposed to be a representative metric of the original data set. So that being the case, 10.83 cannot qualify as a representative value of the original data set, wherein we have the majority of the data points lying between 1 and 5. So this is the drawback with mean. So it's very easy to calculate, no doubt about it. But then the problem with mean is it would get easily influenced by the presence of outlier or extreme value in the data set, right? So that we need to remember. So if you have an outlier or extreme value in the data set due to some assignable or special cause variation, we cannot use mean as a measure of average or measure of central tendency. We need to use median as a measure of average or measure of central tendency. So how will you calculate median? So median can be calculated manually simply by arranging the data set in an ascending or descending order and picking the central value. So once we arrange the data set in an ascending or descending order, the central value in the data set will be considered as median, right? But then if you have even number of data points, so like including the outlier, we will have 6 data points in the data set, right? So that is nothing but even number of data points. So when we have even number of data points, we can understand that there will be 2 central values. And the average of these 2 central values will be considered as median. So let us calculate median without outlier and median with outlier and see whether median as a metric gets unduly influenced by the presence of outlier or not. So first I'm going to calculate median without the outlier value. So I'm going to consider only 1, 2, 3, 4, 5. That's it. Right? So it is already arranged in an ascending order. So I don't have to sort the data set. So when it is only 1, 2, 3, 4, 5, what will be the central value? The central value will be 3, right? So if it is only 1, 2, 3, 4, 5, odd number of data points, we can easily pick the central value, correct? So 1, 2, 3, 4, 5, the central value will be 3. So this 3 actually divides the data set into two equal parts. So 1 and 2 on the left-hand side, 4 and 5 on the right-hand side. So 3 is the central value and 3 will be your median. But then let us calculate median with the outlier value. So median with the outlier. So I'm going to include 50 as well. Now, again, the data set has already been arranged in an ascending order. So no need to sort this data set. So when we have even number of data points, as I told you, there will be two central values. So what are the two central values in this data set? When we have 3 and 4, right? So the average of these two central values will be your median. So how will you calculate the average of these two central values? 3 plus 4 divided by 2, 3.5. So as we can see, because of this outlier value, mean has gone up from 3 to 10.83. But median has gone up from 3 to 3.5. That's it. 3.5 can still be considered as a representative value of this data set, where majority of the data points are lying between 1 and 5, right? So there is a learning here. So mean gets influenced by the presence of outlier. Median doesn't seem to get unduly influenced by the presence of outlier or extreme value. So in case your data set contains outlier or extreme value, we need to use median as a measure of central tendency or median as a measure of average. Clear when to use mean, when to use median. Now the third metric that we have is mode, right? What is mode? Mode is nothing but the most frequently occurring data point in a data set. Say for example, you have a data set like this, 1, 1, 2, 2, 2, 3, 3, right? So you have a data set like 1, 1, 2, 2, 2, and 3, 3. So what will be the mode of this data set? The mode will be 2, because 2 is the value that is occurring maximum number of times in this data set. So mode will be 2. So when can we use mode as a measure of average? When we are dealing with rank order data or rating data. Say for example, in a customer satisfaction survey. So the customer would be asked to provide a rating in the scale of 1 to 5 for some questions asked in the survey, right? So question number 1, majority of the customers have provided a rating of 3. So what would be the average score, average rating score for that particular question? It will be 3 because we need to calculate mode, right? So mode will be 3. So for question number 2, majority of the customers have given 4 as the rating. So what will be the mode for that particular question? It will be 4. So 4 will be considered as the average rating score for question number 2. So mode as a measure of average, we need to remember, should be applied when we deal with rating data or a rank order data. But in a practical scenario, most of the people will use mean to calculate the average value for a rating data. So that is not the correct way. So we need to use mode as the metric here, right? So these are the three measures of central tendency or location. So that is what I have summarized here. So mean is a simple arithmetic average and is very easy to calculate. But the disadvantage with mean is that it would get easily influenced by the presence of outliers or extreme values in the data set. So hence, mean as a metric cannot be used if there is an outlier or extreme value in a data set. So when we consider only 1, 2, 3, 4, 5 as the data set, we see mean and median have the same value. There is no problem at all. So only when we have the outlier present in the data set, we see different values for mean and median, right? So when we don't have outlier in the data set, we will have a scenario where mean and median will be the same. But when we have outlier in the data set, so mean and median can be different. So if you look at median, so if you have a outlier value in the data set, then which metric we need to use for measuring the average? we need to use median. So how to calculate median? So this is calculated manually by arranging the data set in an ascending or descending order and picking the central value. But then as I told you, if you have even number of data points in the data set, there will be two central values. The average of these two central values will be your median. And as I told you, mode is the most frequently occurring data point in a data set, and mode as a measure of average can be deployed for if you are dealing with rank order data or rating data. The second set of metrics that we have under descriptive statistics, the measures of variation. Again, we have three measures of variation. So the first one is range, and then we have variance, and the most popular one, standard deviation. So if you want to quantify the variation in a data set, these are the matrices that we need to apply. So range, variance, and standard deviation. Again, let us consider a very simple example and see how to calculate all these matrices and also understand the characteristics of all these matrices. That is very, very important. Calculation is not a big thing. As I told you, we have all these formulas. Even if you are finding it difficult to apply a formula and then perform the calculations, we have the template, right? So you can use the template and then get the answer. But the characteristic of all these matrices, right, is very, very important. So we need to learn. So what are the characteristics of these matrices? So that is going to be important so that we are able to apply these matrices in for relevant scenarios, right? So which metric needs to be used for what type of scenario? So that is something that we will be able to clearly understand if you are able to learn the characteristics pertaining to each of these matrices. So again, let us consider a simple data set 1, 2, 3, 4, 5. So how will you calculate range for this? Range is a very, very simple calculation, is the difference between the maximum and the minimum values in the data set. So range is nothing but the difference between the maximum and the minimum values in the data set. So here, what is the maximum value? 5 is the maximum value. What is the minimum value? 1 is the minimum value. So 5 minus 1, range will be 4. Simple, very easy to calculate. But then let me apply the Excel formula here, is equal to max of this data set minus minimum of this data set will give me the range, right? 4 is the range. So the problem with range is it doesn't consider all the other values in between the maximum and minimum values for its calculation. So as we can see, range considers only the maximum and the minimum values for its calculation. So it doesn't consider all the other values in between the maximum and the minimum values for its calculation. So if you look at this example, it is considering only 1 and 5 for calculation. So it has left out 2, 3, and 4, the values in between the maximum and the minimum values from its calculation. So hence, range as a measure of variation can be applied only if the data set contains 6 or less than 6 data points. That is the rule, right? So because it's very easy to calculate, it doesn't consider all the other data points other than the maximum and the minimum values in a data set, and hence range as a metric can be applied only if the data set contains 6 or less than 6 data points. But then if the data set contains more than 6 data points, then we need to apply either variance or standard deviation. So the basic calculation that is involved for calculating these two matrices, variance and standard deviation, is pretty much the same. But standard deviation, we can say, is a simplified version of variance. So standard deviation is one step further to variance. But the base calculation is pretty much similar for both these matrices. So let us try to understand these two matrices by considering the manual formula which we can apply for calculating the variance and standard deviation. So variance, how will you calculate? It is nothing but summation. So summation, the symbol is this. This is summation symbol. Summation of square deviation. So put two brackets and then to the power of 2. That means we are squaring it. Deviation, you will represent it by a negative sign. So summation of square deviation of each and every data point in the data set. So let me denote each and every data point in the data set as xi. So xi, so each and every data point in the data set from the mean value. So the mean value will be denoted by this notation x bar. So x bar stands for sample mean. So all these things you need to know as a black belt. So x bar is the sample notation for mean. So we are talking about the square deviation of each and every data point in the data set from the mean value. So I told you, right, when we discussed about the concept of variation, what is variation? Variation, I told you, is any deviation from the standard. So here we are considering the mean value as the standard value. So any deviation from the standard is what we would calculate as variance, which is one of the variation metric. So the deviation of each and every data point from the mean value is what has been projected as variance. So the entire thing will be divided by sample size, which is again denoted by this notation small n. Small n stands for sample size. So n minus 1 in the denominator. So this is how we would calculate the variance applying the manual formula. Again, no need to by heart any of these formulas, right? So this manual formula, I have actually mentioned it here just to make you understand the concept of variance. That's it. So you'll be able to understand the concept of variance and standard deviation through this manual formula. So that is why I've introduced the manual formula, not for by hearting it or not for applying it in the future. Okay. So let me just calculate the variance using this manual formula. So for that, first and foremost, we need to calculate the mean value. So what is the mean value for this data set? We already calculated. So sum of all these data points divided by the total number of data points, which is 3, right? Fine. So let me just calculate the variance. So how will you calculate? So the first data point, 1 minus 3, and we need to square it, right? So the deviation of each and every data point from the mean, and we need to square it. So summation means we need to keep adding. So the second data point in the data set, 2 minus 3, the whole square, plus 3 minus 3, the whole square, plus 4 minus 3, the whole square, plus 5 minus 3, the whole square, right? So the entire thing will be the numerator, whole thing divided by n minus 1. How many data points are there in the data set? 5 data points. 5 minus 1, 4 in the denominator. That's it. 2.5 is the variance. Now what we can understand through this value? So variance is nothing but the average of the deviation or the average deviation of each and every data point from the mean value. So I can say each and every data point on an average is located at 2.5 distance from the mean, right? And one more thing that we need to clearly understand here is when we square all these deviations, right? So the deviation of each and every data point from the mean, when it is getting squared, even the negative deviation will become positive, right? So through this formula, we can clearly understand that variance and standard deviation cannot take negative values, right? So generally speaking, all these variation matrices will not take negative values. Even if you have negative values in the data set, we are only quantifying the variation there. That's it. We are not, looking at whether the variation is occurring on the positive side of the scale or on the negative side of the scale. Clear? So the formula itself clearly, helps us to understand that logic. So when we are going to square each and every deviation, right? So we will get only positive values. So 1 minus 3, if you are going to leave it as it is actually minus 2. But when we square this minus 2, it will become plus 4. So here, if you look at the variance formula, we are squaring the deviation of each and every data point from the mean value. So when we square it, even the negative deviations will become positive. So through this, we can clearly understand that the variation matrices cannot take negative values. It can take only positive values. So what is standard deviation? As I told you, standard deviation, the base calculation is pretty much similar like variance, but standard deviation will go one step further. So standard deviation is the positive square root of variance. So simply take square root of this variance value, you will get the standard deviation. That's it. All right. So when I say positive square root, you need to understand. So square root of a value can be both positive and negative values. Square root of 9 is plus or minus 3. Square root of 16 plus or minus 4. Square root of 25 plus or minus 5. Square root of 36 plus or minus 6. So for standard deviation calculation purposes, we will consider only the positive square root value of variance, right? Because standard deviation as a variation metric cannot take negative values. So we have already seen why it cannot take negative values, because the formula for calculating the variance, when we square the deviation of each and every data point from the mean, even though it is a negative deviation, when we square it, it will become positive, right? So the least value these variation matrices can take is 0, provided all the data points in the data set are same. Say we have a data set 1, 1, 1, 1, 1. So there is no variation at all. So there is no difference in the numerical values in this data set. So there is no variation at all. So only if there is some difference in the numerical values in the data set, we will say that there is some variation. So when we have all the data points being same, so that means there is no variation at all. So all these variation matrices will be 0, right? So even if you provide negative values, say I am calculating the variance for this data set, -1, -2, -3, -4, -5. So if you see mean will consider that negative value. So mean will take that negative value. But if you look at variance and also standard deviation, it will still be positive value, right? So they cannot take negative values even though we have negative values in the data set. So what these variation matrices actually perform here is they simply quantify the variation. That's it. Whether it is happening on the positive side of the scale or on the negative side of the scale, it doesn't really get unduly influenced due to that, right? So it only calculates the quantum of variation, right? So that is what it is. So even if you have negative values in the data set, we will still get the positive values as variance and standard deviation. Fine. So this is how we would perform all these calculations. Let me just look at the summary here. So as I told you, range is very easy to calculate and is the difference between the maximum and the minimum values in a data set. But the disadvantage with range is that it doesn't consider any other value in between the maximum and the minimum values in a data set, and hence range as a measure of variation can be applied only if the data set contains 6 or less than 6 data points. So if your data set contains more than 6 data points, then we need to apply either variance or standard deviation. So both variance and standard deviation would indicate the average distance of each and every data point from the mean value, right? So there can be a question on this. Let me just make this in bold font. So what does, variance indicate? So we need to pick this option, the average distance of each and every data point in the data set from the mean value is what we would call as variance, right? So both variance and standard deviation, as I told you, cannot take negative values, and the least value these matrices can take is 0, provided all the data points in the data set are pretty much the same. And standard deviation, as we saw, is the positive square root of variance. So it is the simplified version of variance. Fine. So there is also Excel formula to perform the calculations. So we'll also get introduced to the Excel formulas side by side. So we have seen the manual formula, how to apply the manual formula and get the answers. Let us also apply the Excel formula and see whether we get the same answers. So for mean, the Excel formula is equal to average. You can even make a note of it. So in case you want to use this in future, you can do so, right? But then as far as our assessment is concerned, there is no need for you to apply any of these formulas. So we have the templates for all those questions that are likely to be part of the assessment, right? So you don't have to really worry about applying the formula, but just you can learn, what would be the Excel formula for calculating all these matrices. So for mean, the Excel formula will be is equal to average. As I told you, the Excel formulas will always start with equal to sign. Moment you put that equal to sign, the Excel will understand you are trying to write a formula. So for mean, it will be is equal to average and then open bracket, provide the range of the data set. So first without the outlier, so get the value 3 and then with the outlier value. So is equal to average and then give the range of the data set including the outlier value. That's it, right? You don't have to really, sum up all the values and then divide by the total number of data points. That is the manual calculation, right? So when you apply the Excel formula, you straight away, incorporate the string that we need to use as the Excel formula. So for mean, it will be equal to average and provide the range of the data set. That is enough, right? And for median, so the manual formula, I told you we need to arrange the data set in an ascending or descending order and pick the central value. So when you apply the Excel formula, there is no need for you to arrange the data set in an ascending or descending order. The Excel will take care of all those things at the back end. So you don't have to really worry about. Here it is already arranged in an ascending order, so no problem, right? Even if the data set is not arranged in an ascending or descending order, for calculating the median, if you are applying the Excel formula, we can straight away apply it as it is. We don't have to really sort it in a ascending or descending order. So median is equal to median is the Excel formula, right? And we need to give the range of the data set. So first without the outlier value, so we get the value 3. And the next one with the outlier value. So I apply the formula is equal to median and we need to include the outlier value as well. 3.5. So when we, applied the manual logic to perform the calculation, I told you we need to arrange the data set in an ascending or descending order. If there are even number of data points, there will be two central values. Average of those two central values will be considered as median. But when we apply the Excel formula, you don't have to really worry about picking those two central values and calculating the average value for those two central values, etc. The Excel formula will give the final answer for median. Right? So simple. And then for mode, the formula is equal to mode and then give the range of the data set. Is 2, right? Range, we don't have any specific Excel formula, so we need to use the manual formula in Excel. But for variance, the Excel formula is equal to VAR dot S. When I put VAR dot S, that means we are calculating variance for a sample data set. So VAR dot S and then provide the range of the data set. So there is no need for you to calculate the mean and then calculate the square deviation of each and every data point from the mean and then summing it up. Nothing of that sort need to be performed. Straight away apply the Excel formula is equal to var.s and provide the range of the data set. That's it. You'll get to see the variance value. And for standard deviation, so I told you when you are calculating using the manual formula, so for calculating the standard deviation value, we need to first calculate the variance and then, obtain the square root value for that variance as standard deviation, right? But then if you are applying the Excel formula, there is no dependency on variance for calculating the standard deviation. We can use an independent formula for calculating the standard deviation. So the formula, Excel formula is equal to STDEV dot S. That means we are calculating standard deviation for a sample data set. So is equal to STDEV dot S, and then we need to provide the range of the data set. That's it. Get the standard deviation value. So this is how we would apply the Excel formula and perform all these calculations. Now let us go to the exercise file. So this file I had actually shared with you all on the first day, at the end of the first day's training. So it will be an empty file. So we are going to solve all these statistical exercises that are part of this Excel file, right? So the first sheet that we have is descriptive statistic sheet. So for most of the statistical concepts, right, I would have also given the Minitab path at the top. And apart from that, I would also given the detailed procedure as to how to perform the calculations using the Excel formula, the manual formula, and also how to navigate through Minitab, which you are going to see shortly, and perform the calculations. So descriptive statistics measures, I have given the detailed process steps to perform the calculations using the Excel formula as well as using Minitab. Now we have this exercise number 1 wherein we are provided with the processing time data and we have been asked to calculate the descriptive statistics measures. So we have some 30 samples, right, for which we have the processing time data. So we have, 30 processing time data points, right? So for this data set, we need to calculate the descriptive statistics measures. Again, for a meaningful statistical analysis, please do remember that we need to have minimum of 30 sample data points. So anything less than 30, it will be too risky for us to analyze and then come up with the inference. So we need to have minimum of 30 sample data points. But then there are few exceptions, for this particular rule. So there are a couple of statistical concepts where we can analyze even with less than 30 sample data points. For majority of the statistical concepts, we need to have minimum of 30 sample data points to even perform a meaningful analysis. Clear? So we have 30 sample data points, so no problem. So how will you calculate mean? Applying the Excel formula, so is equal to average, and then provide the range of the data set containing the processing time data. Cover all the 30 data points. So 5.2 is mean. So how will you calculate median? As I told you, if you're applying the Excel formula to calculate the median, then there is no need for us to arrange the data set in an ascending or descending order. So here if you see the processing time data set, it has not been arranged in an ascending or descending order, right? So we can leave it as it is and straight away apply the Excel formula to calculate the median. So is equal to median and then provide the range of the data set. That's it. So we get the median value also as 5.2. So if both mean and median are same, what can we infer from this? Anyone? If both mean and median are same.
There
So
are
what?
no outliers.
Very good. So there are no outliers in this data set, right? So you don't even need to perform some calculations to identify if the data set contains any outlier or not. So when mean and median are same, we can straight away infer that there are no outliers in this data set. Fantastic, right? So if mean is going to be greater than median, then we can understand that the outlier value is on the upper side of the data spectrum. Just like how we saw in this example, 1, 2, 3, 4, 5, and suddenly we had 50 as the outlier value. So this 50 is on the upper side of the data spectrum, right? So here is a situation where mean will be greater than the median, right? But then if you have the outlier value on the lower side of the data spectrum, then mean will be less than the median, right? Say, for example, all the other data points are in and around 50. Suddenly you have a data point which is like 7 or 8. So 7 or 8 will be considered as an outlier value on the lower side of the data spectrum. So that can also happen. The outlier need not be necessarily lying on the upper side of the data spectrum. It can also lie on the lower side of the data spectrum, which is quite possible. So in that case, we will have mean less than the median, right? So these are all some of the things that we can actually infer straight away by looking at the mean and median values, fine? And mode is the most frequently occurring data point in the data set. So I give the formula is equal to mode and then provide the range of the data set. That's it. So mode is also 5.2. So if you have all the three measures of central tendency with the same value, so what we can infer from this is this data distribution is normal, right? So what we can infer from this, the data distribution is normal. So the processing time data distribution is normal, right? So what exactly is normal distribution? We learn, right, in the days to come. So there is a separate section called probability distribution, which we are going to learn as part of the measure phase. There we are going to learn about normal distribution. But this is one indication. So if you have the measures of central tendency having the same value, then we can infer that the data distribution is normal. Mean and median are same, we can infer that there are no outliers or extreme values in the data set. Now, for calculating the range, as I told you, we need to apply the manual formula in Excel. So is equal to maximum of the data set minus minimum of the data set. So this will give the range. Maximum of the data set minus the minimum of the data set. And for variance, the Excel formula is equal to VAR dot S, and we need to provide the range of the data set. And for standard deviation, it will be is equal to STDEV dot S, and we need to provide the range of the data set. So if you want, you can also parallelly work with me, at least the Excel formula part. I'll also show you how to navigate through Minitab and perform all these calculations. But then in Excel, we also have what is called as data pack. But that is something, which will not be included as a default package. So we need to go to options and then include that data pack. So if it is not included in your Excel, so if you are listening to this for the first time, obviously you wouldn't have included it. So what we need to do, we need to go to File, and there is something called Options, right? So click on Options, and then there is a menu called Add-ins. Just click on Add-ins, and you will see Analysis Tool Pack as the first add-in. Just highlight on that and then kind of say Go and OK. So moment we click on Go and OK, this Analysis Tool Pack will get added as one of the Excel menu. So that you can find in this data tab. So the data tab, you see data analysis, right? So this is that analysis tool pack. So click on this data analysis. You will have all these statistical tools available as a menu in this data analysis pack. And we want to calculate the descriptive statistics measures. So just click on descriptive statistics and click OK. And the dialog box will open. So we need to provide the input range of the data set for which we are calculating the descriptive statistics measures, right? And you want the output range to be provided in the same worksheet. So let me just go to a corner and then provide the output range. Right? And then we click OK. Right? So we have all these descriptive statistics measures. So we'll only consider those which we have already learned, right? Let us not be bothered about the other matrices. So mean is given as 5.2, right? And the median is also 5.2, mode is also 5.2. And then the standard deviation is 0.1114, right? And then the variance is 0.0124, right? And the range is 0.4. The rest of the metrics, let us not even consider, right? So these are the descriptive statistics measures. And these are the values that we actually obtained using the Excel formula here. Clear? Now we will look at how to perform the calculations using Minitab. So this analysis tool pack will be very, very useful. Only thing is we need to have the raw data set available for using this analysis tool pack, right? So we need to have the raw data set available. So if you have a summarized values provided, then we cannot use this analysis tool pack. So we need to have the base data available with us, which will be the case when you actually work on a project exercise. So you can make use of this analysis tool pack. So that's why I told you there is no need for depending on Minitab to perform all these calculations. So we can use Excel and then perform all these calculations. But then as far as our assessment is concerned, even this, kind of an effort need not be put. So as I told you, for those statistical exercises that are likely to be asked as questions in the final assessment, I've already provided you with the template. You just need to learn how to input the values in the template and interpret the answer. That's it. So let me move over to Minitab. So let me click on Minitab. So this is how the home screen will actually look like, right? Once you click on the Minitab icon, so this is the home screen that you will get. So if you can see, it is actually divided into two sections. The bottom one is like your Excel sheet, right? This is what we would call as the worksheet. And this Excel sheet is where we would actually input all the values, right? So whatever input values we need to incorporate, we will feed them in this Excel sheet, right? So the Excel sheet has also got a row which is completely shaded in gray. So the topmost row in the Excel sheet is completely shaded in gray. And this is the row wherein we are supposed to provide the column headers. So if you are going to, input any numerical value in this gray shaded row, it will not be considered for your analysis or for your calculation. So this gray shaded row is reserved for providing column header names. And you should actually start inputting values only from row number 1, as we can see here, right? So this is the Excel sheet wherein you provide all the input values. So the top section is a blank space where you'll get all the answers. So the output values will appear in this blank space. And right at the top, you have various tabs here, right? So these are the tabs that I will navigate and then provide directions to Minitab to perform necessary analysis, right? So these are the tabs that I'm going to navigate and provide directions to Minitab to perform necessary analysis. So as part of our curriculum, we'll be predominantly using Calc, Stat, and Graph. These are the three tabs that we'll be using quite extensively as part of our training session, right? So for descriptive statistics measures, so first and foremost, we need to copy paste the entire table in the Minitab worksheet. So let me just copy paste the entire table in the Minitab worksheet, right? And for calculating the descriptive statistics measures, we need to go to Stat, Basic Statistics, and we have a menu called Display Descriptive Statistics. So Stat, Basic Statistics, Display Descriptive Statistics, and the cursor will blink inside the variables field. So here we need to provide the column reference for the input values for which we are calculating the descriptive statistics measures. So we are going to calculate the descriptive statistics measures for the processing time data set. So we need to provide the processing time column header reference inside this variables field. So for that, we simply need to double click on this column header here. So the left-hand side pane will contain the columns wherein we have entered all these numerical values. So even the samples, right, are the numerical values which we have entered apart from the processing time. So a couple of, column headers are displayed here. So we need to choose the processing time column header because we are calculating descriptive statistics measures for this processing time data set. So double click on that processing time column header, it would automatically appear inside this variables field. And then we click on statistics and choose the descriptive statistics measures that you want to calculate, right? All the other things I will remove. I will have only those descriptive statistics measures which I want to calculate. So this is a older version of Minitab software, so we don't find mode as a statistical metric here. But as we all know, mode can be easily calculated by applying the Excel formula. All the other matrices will get displayed. So you click OK at both the places. You get to see the descriptive statistics measures displayed in this output section. So mean is 5.2, standard deviation is 0.1114, variance is 0.0124, median is also 5.2, and the range is 0.4. This is exactly what we got applying the Excel formula, right? So this is how we would perform the descriptive statistics measures calculation. Fine. So I'll go for a 50-minute break. So when we come back, we look at the next section, graphical representation of data. And then we will revisit the same exercise because for the same exercise, we are going to perform some advanced calculations. And also we are going to look at how to construct the appropriate graphical formats as well, right? So that will be after a 15-minute break.
शाइनी या वार्म रिंग को कितना डिस्क्राइब करेगा the ice cream was very tall and cold Richie or cold butterfly. Which one is correct? Richie. Rich. Awesome. Hungry mouse is the cheese. Each आएगा कि hungry आएगा? Eat on the साफ, बहुत साफ चीजों में जैसे this house is very neat. This classroom is very clean. ठीक है? तो मैं classroom में describe कर रही हूँ. Classroom तो बहुत neat है, बहुत clean है, right? A big or a funny clown at the circle. Then is the correct clown has real funny. Here was a large tree in the park. अगर तो park देखेगा तो क्या चलता है कि ये भी बड़ा होता. Here is a large tree in the park. Here is a big tree in the park. So large, big tree. Actually describe the tree वाले describe. What color? कौन सी describe कर सकते हैं? This tree is a which color? Yellow. It bears yellow flowers, right? 1, 2, 3. 3 people are sitting in the park. है ना? तो describe कर सकते हैं. इस पिक्चर में देख के क्या सकता है? Tree है, tree बहुत big है. It has the yellow flowers, right? People are sitting under the tree, isn't it? So इस तरह से describe कर सकता है. होना क्या? Cold का क्या आएगा? Match कर. Opposite है, opposite. Cold opposite नहीं है, मतलब वो है. Clear ना? Cold का क्या आएगा? Cold chili. चलता माता वाह माता there are 2 major magic you that open any food with one word is thanks and another word is please. सबसे गंदा लगता है. one little word is this and this. So there are two little magic words, right? One word is this, please. Okay, so these are the and Pachara potato circle. Correct. These all are adjectives. Here I have shiny, gold, pretty, amazing. These all words are what? Feminine. Adjectives, right? All words are adjectives. As have our adjective, ever. Circle the right action word. Anita sings या dances many songs. Yeah, sings, dances many songs. Songs की तरह. इस तरह ना songs. You sing songs, I sing songs, she sings songs. So sing. बात तो बड़ी वाला सुन रहा था. We read or sing book in the we sing the band sings calls for the class to begin. Tally की करती है. Links करती है, calls करती है. Links करती है. पहले हमेशा think करे. Talk or write in there. And the One, two, three, four, five. Once I caught a fish alive. 7, 8, 9, 10. Six, 7, 8, 9, 10. Go. So it with my finger. So go the Take sound. Duck ਦੀ sound ਕਿਹੜੀ ਹੁੰਦੀ ਹੈ? Dog ਦੀ sound ਕੀ ਹੈ? Cat ਦੀ a bird can fly. पूरा काम किया fly करना. So frog can go. Peacock is dancing. The mountain is moving. So a move word, dance word, सारे action words. Yeah. The voice goes or flies the kite. क्या आएगा? Goes the kite or flies the kite. Voice की होती है. Flies the kite fly करते हैं. It flies की है. Flies की है. The girl rides or holds a pink cycle. Because to be a girl rides. Yeah, action verbs. She takes or rings the bell. Rings the bell. हमेशा bell की करेगी ringing करेगी. The boy told or runs the kite school. करेगा. Hold करेगा फिर run करेगा kite school. Kite school लता का होता है तो पकड़ना पड़ता है. ठीक है? पूरा पक्का चलाओ लेकिन
हेलो
लो यार तुसी तो
ਹੈਗੀ ਮੇਰੀ ਆ ਦੇਖ ਪਤਾ ਨਹੀਂ ਕੀ ਕਰਦੀਆਂ ਕਦੀ ਇੱਧਰ ਕਦੀ ਉੱਧਰ
ਇਹਨੂੰ ਨੀਚੇ ਰੱਖੋਗੇ ਦੋਨਾਂ ਚੀਜ਼ਾਂ ਬਸ ਨੀਚੇ ਰੱਖ ਦਿਓ.
ਇੱਥੇ ਹੀ ਰਹਿੰਦੇ ਮੈਂ ਰੱਖ ਦਾਂਗਾ
और ਇਹਨੇ ਸੋਣਾ ਨਾ ਤਾਂ
ਹਾਂ ਤਾਂ ਕੋਈ ਨਹੀਂ ਕੁਛ ਨਹੀਂ ਹੁੰਦਾ ਸੋ ਜਾਏਗਾ
ਮੰਮਾ ਕੀ ਕਰਦੀ ਹੈ ਬਹੁਤ ਕੰਮਾਈ. What you're doing tea ਦੇ ਨਾਲ have ਨਾ we are having tea having drinking ਹੁੰਦਾ milk ਦੇ ਨਾਲ we are drinking milk. Water we drinkers walking back. Yes. Tell the story. The story of this. Right? Is going to tomorrow. Going is also action verbs.
Hello, friends. I'm back. Hope you're all back as well. So let us continue. So let me just share my screen. Right. So we looked at how to calculate the descriptive statistics measures using the Excel formula and also navigating through mini tab. Now we look at the graphical representation of data. And after that, as I told you, look at the same exercise and see how to construct the graphical formats for this particular scenario. So let us go back to the notes file and we are going to look at the next section, this graphical representation of data. So the first graphical format that we are going to see is histogram. So histogram is the appropriate graphical format for representing continuous data. So I told this very clearly that we need to identify the data type correctly at the beginning of the project exercise because there are separate set of statistical tools and techniques applicable for a particular data type, right? So here itself, it has started. So we can see histogram is the appropriate graphical format for representing continuous data. So if you have discrete data, we cannot construct histogram for that scenario. So how this histogram will actually look like? So histogram will contain an x-axis and the y-axis. So it is a graphical format. So it will contain x-axis and the y-axis. So along the x-axis, we will have the class intervals for the continuous data. So along the x-axis, we will have the class intervals for the continuous data. And along the y-axis, we will have the scale for the frequency distribution. So frequency distribution is nothing but the number of data points that would actually fall in a particular class interval. So number of data points in the data set that would actually fall in a particular class interval is what we would call as the frequency distribution. So we will roughly construct the histograms. So the main idea is to understand what are all the things that we can actually identify by looking at a histogram. But the actual histogram we will construct for this processing time data set in a short while. So let us consider this processing time data set and let me just, come up with the class intervals. But then we will not, derive the frequency distribution of each and every class interval uh, by looking at the data points in this processing time data set. We are going to do a rough estimate with regard to the frequency distribution, but then I will show you how to construct the class interval. So for that, we need to first identify what is the maximum value and the minimum value in this data set. So the minimum value and the maximum value. So the minimum value can be obtained by using the formula is equal to MIN and then provide the range of the data set. Right? And then maximum value. So the minimum value is 5 and the maximum value again is equal to MEX and then provide the range of the data set. Right? It is 5.4. So 5 is the minimum value, 5.4 is the maximum value in this processing time data set. So the first class interval will start with 5. So it can be from 5 to 5.1. And then the second class interval can be from 5.1 to 5.2. And then from 5.2 to 5.3, 5.3 to 5.4, 5.4 to 5.5. So even though the maximum value that we have in this data set is 5.4, if you have a value 5.4 in the data set, it would actually fall in the final class interval, 5.4 to 5.5, because the previous class interval, 5.3 to 5.4, will end with 5.3999, etc. Right? It is still not at 5.4. So 5.4 as a value would ideally fall in the final class interval. So that is why I have created one more class interval at the end, 5.4 to 5.5, right? But then 5.1 as a value in the data set would fall in the second class interval, 5.1 to 5.2. 5.2 as a value in the data set would fall in the third class interval and so on, right? So for these class intervals, we need to draw adjoining bars coinciding with their frequency distribution value for which the scale is given on the y-axis, right? Say, let me assume the frequency distribution values. So let me assume that there are a couple of data points in the data set that would lie between 5 and 5.1. So I will draw a bar coinciding with 2 on the y-axis like this. And suppose, I find something like, 8 data points lying between 5.1 and 5.2. I will draw an adjoining bar coinciding with 8 on the y-axis. Suppose I find 12 data points lying between 5.2 and 5.3. So I will draw yet another adjoining bar coinciding with 12 on the y-axis. So this will be 2 plus 8 plus 12. So 22 data points have already been considered. So out of 30, we have already considered 22 data points. We have only 8 data points available. So the next class interval 5.3 to 5.4, let me assume that there are 6 data points in it. So I will draw another adjoining bar coinciding with 6 on the y-axis. And the final class interval 5.4 to 5.5, let me assume that there are a couple of data points. So I will draw yet another adjoining bar coinciding with 2 on the y-axis. Now, if you total the frequency distribution values for all these class intervals, it should come to 30. So 2 plus 8, 10, 10 plus 12 is 22, 22 plus 6 is 28, and 28 plus 2 is 30. So we have considered all the 30 data points in the processing time data set. As I told you, we're just making an assumption with regard to the frequency distribution value for each and every class interval. So we have not, really looked at, a particular data point and see which class interval that data point would actually fall. And then finally count the number of data points that would fall in a particular class interval. So that is the way we need to proceed with this exercise. But then since we are going to see how to construct the histogram using Minitab and Excel, so we are not taking pains to construct it manually. But then we need to understand, what are all the various aspects that we can actually identify by looking at the histogram. So that is why I drew this histogram, considering some imaginary frequency distribution values, right? And if you are going to connect the midpoints of all these adjoining bars in the histogram, we will get what is called as the bell curve. So this is what is called as a bell curve. And if this bell curve is symmetric, right? That means if you are going to cut the bell curve into two equal halves, the left-hand side image is a mirror image of the right-hand side, then we would call that bell curve as a symmetric bell curve. So if the bell curve is more or less symmetric, then the data distribution is considered to be normal. So this we already seen. If the uh, three measures of central tendency have the same values, then in that case, we can infer that the data distribution is normal. So another inference that we can actually come out with regarding the normality of the data distribution is by looking at the shape of the bell curve. So the bell curve that we would draw after constructing the histogram is going to be symmetric. Then we can infer that the data distribution is normal. But then if you are going to get a bell curve like this, which has a longer tail on the right hand side or a longer tail on the left hand side. So these are called as skewed distributions or non-normal distributions. Skewed distributions, right? So when can we get a scenario like this, wherein we will have a longer tail for the bell curve on the right hand side or on the left hand side, when we have these outlier values existing in the data set, right? So if you look at the example that we saw, 1, 2, 3, 4, 5, and 50. So 1, 2, 3, 4, 5 will actually fall in this particular area, and 50 will be somewhere on the right extreme, right? So the bell curve will have a longer tail on the right hand side. So if it has a longer tail on the right-hand side, we can understand that the outlier value is on the upper side of the data spectrum, and we would call this bell curve as positively skewed. But then if you have a longer tail for the bell curve on the left-hand side, it would mean that the outlier value is on the lower side of the data spectrum, and we would call this as negatively skewed. So this will be positively skewed and this will be negatively skewed. And all these skewed distributions which can happen due to the presence of outlier in the data set will be termed as non-normal distribution. So only if it is a normal distribution, we can consider mean as a statistical metric for central tendency. If it is a non-normal distribution, which would occur or which would actually be evident in case of any outlier present in the data set, we need to use the statistical metric called median, right? So this is the thumb rule. So mean as a statistical metric can be applied if the data distribution is normal. But then if the data distribution is non-normal due to the presence of outliers present in the data set, we need to use the statistical metric called median. Now, what are the three things that we can actually identify by looking at a histogram? So number one, we can identify the spread of the distribution. Spread is nothing but the variation or the range of the data set, right? So here we can look at the width of the bell curve and then understand what is the spread of the data distribution. So it ranges from 5 to 5.4, right? That you can easily find out by looking at the width of the bell curve. So that is the first thing that we can identify by looking at a histogram. So if the variation is less, that means the process performance is highly consistent. If the variation is huge, which can be looked at from the width of the bell curve in the histogram, we can understand that the process performance is not all that consistent, right? The second thing that we can identify is the shape of the distribution. So whether it is, symmetric or skewed distribution like what we just now saw, right? So if it is symmetric distribution, we can understand that the data distribution is normal. If it is a skewed distribution, we can understand that the data distribution is non-normal. So when can we get a skewed distribution? When we have the presence of outliers in the data set. So if the outlier is on the upper side of the data spectrum, we will get a longer tail for the bell curve on the right-hand side. We would call this as positively skewed. On the other hand, if you have the outlier value on the lower side of the data spectrum, we will have a longer tail for the bell curve on the left-hand side of the data spectrum or on the lower side of the data spectrum, which we would call it as negatively skewed. And the third thing that we can identify by looking at the histogram is the class interval, which is likely to contain the average value. So the class interval with the tallest bar is likely to contain the average value. So it is quite obvious, right? So class interval is having the tallest bar means what? So most of the data points in the data set are actually lying in between those two interval values. So obviously the average value also would be uh, in between those two interval values. So we can easily identify that. So the class interval which is likely to contain the average value can be easily identified by looking at the histogram. So the class interval with the tallest bar is likely to contain the average value. So the only drawback with histogram is that we won't be able to capture the time orderliness of the data points. So if you look at the data set, right? So we will not be able to capture whether a particular data point occurred first or second or third or fourth or fifth and so on, right? So 5.1 as a data point will get merged in the second class interval. 5 as a data point will get included in the first class interval. 5.4 as a data point will get included in the final class interval, right? So once we construct the histogram, we will not be able to understand the sequence of the data points. So which data point occurred first, second, third, and so on, right? So the time orderliness of the data set cannot be captured by looking at the histogram. So that is the only disadvantage. Fine. So this is about histogram, which is the graphical format for continuous data. So since processing time is a continuous data, so we will see how to construct the histogram for this data set using both Minitab as well as Excel. Now look at the next graphical format, which is bar chart. So if histogram is the appropriate graphical format for representing continuous data, bar chart is the appropriate graphical format for representing discrete data, right? So bar chart is the appropriate graphical format to represent discrete data. So we have a data provided here with regard to the number of units produced by each and every employee in the team. Suppose you want to depict this graphically, since number of units produced is a discrete data. So we need to use bar chart to actually project this graphically. So we need to go to, so how to construct bar chart in Excel? So first we need to highlight the entire table containing the input values, and we need to go to insert recommended charts, and we have the one with all these bars, right? So we will choose the first one. So this is how the bar chart will actually look like. So it will be separate bars because we are dealing with discrete data. It's not continuous data. So we have the bars constructed for the three associates here. So A1 has processed 250 units. So that will have the tallest bar. A2 has processed 235 units. So that will have the bar with the least height, and A3 with 240 units, right? So like this, we can construct the bar chart. But then if you want to, represent proportions, then the appropriate pictorial format will be pie chart, right? If you want to represent proportions, then the appropriate pictorial format will be pie chart. So is a scenario where we have the various cost elements. Along with that, we have also been provided with the percentage contribution of each and every cost element, right? So here we find the salary cost contributing to 70% of the total cost, and then admin cost is 20%, and the miscellaneous cost is 10%. So if you want to construct pie chart for this particular scenario, we need to first highlight, the entire table, and then go to insert recommended charts. You have the one with the circle here. So this is the pie chart depiction, right? So as we can see, looking at the pie, we will be able to clearly find out which particular, cost element is contributing maximum to the overall cost, right? So here we can easily find out that the salary pie is the largest, right? And we can understand that the salary cost is the maximum out of all the other costs, right? In the sense it contributes maximum to the overall cost. And the next highest contributor is the admin cost. And then finally, we have the miscellaneous cost. So we can have any number of elements and the corresponding percentage contribution. So we can construct the pie chart for that scenario. And the next graphical format that we are going to look at is a very important one called run chart. In fact, line chart that we would have probably constructed quite a good number of times, right, is the simplest form of a run chart. So line chart is the simplest form of a run chart. So when will you construct the line chart? So when we want to depict a process performance over a period of time, irrespective of whether the data type is discrete or continuous. So if you want to project the process performance over a period of time, we will typically use the line chart for that. That we will also call that as a trend chart, right? So we will also call that as a trend chart. So if you want to depict the process performance over a period of time, That means you will have the time zone along the x-axis, right? It could be on an hourly basis, or it could be on a daily basis, or it could be on a weekly basis, or it could be on a monthly basis. So depending on the rate of production, we will have the time zone depicted along the x-axis. So whenever you want to depict the process performance over a period of time, then the appropriate chart will be the line chart or the trend chart, right? So say, for example, you want to uh, kind of depict the performance with regard to accuracy percentage, right? Over a period of time. So you have the month-wise data available for accuracy percentage, M1, M2, M3, M4, etc. And along the y-axis, we will have the scale for the accuracy percentage. So 95%, 96%, 97%, 98%, 99%, and so on. The first month it was 96%, second month 95%, third month it was 98%, fourth month it was 99%, fifth month it was 96%. So you have something like this. So we can just first, plot the dots and then connect all the dots to get the trend. So through this, we can clearly understand, whether the process performance is erratic, is going up and down violently, or the process performance is pretty much consistent, or the process performance is showing an upward trend, or is it showing a downward trend. So all those things we can easily understand by constructing a line chart or a trend chart. So we just need to plot the dots, and after that we need to connect all those dots with the trend chart or the trend line, and we get to see what is the trend like, whether it is erratic, whether it is consistent, whether it is showing an upward trend, whether it is a downward trend. So all those things can be noticed, right? So you might have looked at the uh, stock prices graph, right? So stock prices graph will be a line chart, right? Why it is a line chart? Because we have the depiction of stock prices over a period of time. So every 1 hour, so they will kind of identify what was the stock price, and then they will actually display it in the form of a line chart so that people who are looking at it will be able to clearly understand whether the stock price has remained consistent for a particular stock, or is it showing an upward trend or a downward trend, or it is behaving erratically, going up and down violently throughout the day. So it will be captured on an hourly basis, because you would want to see how the stock performed over a day or whatever, right? So we will have the trend chart projected for that particular scenario. So whenever we want to depict the performance over a period of time, then the appropriate chart will be line chart. So you can just close your eyes and pick line chart, right? Irrespective of whether the data type is discrete or continuous or binary discrete, whatever it is, right? You can straight away use a line chart for that scenario. So it's the simplest form of a run chart. But then run chart, the only difference is the line chart, we will not have any average line at the center. The run chart, we will also have the average line at the center. That's the only difference between line chart and run chart. But then the main objective of creating a run chart is to validate whether the data distribution is random or non-random. So that is the primary objective of run chart. So in a run chart, we will try to validate whether the data distribution is random or non-random. So ideally, you would want the data distribution to be random. So only if the data distribution is random, we can infer that the process is influenced by common cause variation alone. And if the process is influenced by common cause variation alone, then the process performance is also said to be stable or consistent, right? And we can apply Six Sigma tools and techniques only if the process performance is consistent. Again, please do not mistake that if a process performance is consistent, then the process performance is also good. So last week, I think we discussed about this. So a process can also be consistently bad, right? So here we know that the process performance is not all that great. So that is why we have taken it as a Six Sigma initiative. But then we would want the process performance to be consistently bad. Then only we will be able to apply the Six Sigma tools and techniques, because in a Six Sigma, we will be looking at reducing the common cause variation. There should not be any presence of assignable cause variation acting on the process. So how can we ensure that common cause variation alone is influencing the process? Only when the data distribution is random. But then if the data distribution is non-random, due to any of the four non-random characteristics that I have listed here, which are trends, oscillations, clustering, and mixture, then we need to infer that the process is influenced by some assignable or special cause variation, and the process performance is also not stable. So we cannot apply Six Sigma tools and techniques if the process performance is highly erratic or is not stable, right? So how will you find out whether the data distribution is random or non-random? So if it is non-random, then we will have presence of these or any of these four non-random characteristics, that is trends, oscillation, clustering, and mixture, right? But then how to identify the non-randomness in a data distribution? We need to apply these four rules to visually observe and then infer that the data distribution is non-random due to one of these non-random characteristics. So what are the four rules that we need to apply? The first rule, when we observe 6 consecutive data points showing an upward or downward trend, then it will be non-randomness due to trend. So if you find 6 consecutive data points showing an upward or a downward trend, then we would call that as non-randomness due to trend. But then if you have only 5 consecutive data points showing an upward or downward trend, we will not call that non-randomness due to trend. Only when we have 6 consecutive data points showing an upward or a downward trend, we would call that as non-randomness due to trend. 6 and above. It automatically means 6 and above. So moment we find the 6 consecutive data point, showing an upward or downward trend, we can understand that the data distribution is non-random due to trend. Or if you have 8 consecutive data points clustered on one side of the average line, either above the average line or below the average line. So if you have 8 consecutive data points clustered on one side of the average line, we will say that the data distribution is non-random due to clustering. Or if you have 14 consecutive data points alternating up and down the average line, means it is highly erratic, right? So when you have 14 consecutive data points alternating up and down the average line, we would call that as non-randomness due to oscillation. But then if you find two sets of data points getting plotted at two different levels in a run chart, we would call this as non-randomness due to mixture. So these are the four rules that we can apply and visually observe whether the data distribution is random or non-random. Clear? So again, I repeat, what are the four rules? The first one, if we observe 6 consecutive data points showing an upward or downward trend, then it is non-randomness due to trend. Or if you observe 8 consecutive data points clustered on one side of the average line, then it is non-randomness due to clustering. Or if you observe 14 consecutive data points alternating up and down the average line, then we would call that as non-randomness due to oscillation. And finally, if you observe two sets of data points getting plotted at two different levels in a run chart, we would call that as non-randomness due to mixture. That means you have actually combined two different data sets as one single data set. So it might be belonging to two different scenarios within a process. So one data set could pertain to the baseline scenario. Another data set may belong to the improved scenario. So if you are combining those two data sets into one single data set, and if you are going to plot the data points in a run chart, you will get a scenario where the data points would get plotted at two different levels in a run chart, and we can understand that there is non-randomness due to mixture, right? So that means whenever you find non-randomness in the data distribution, we can infer that the process is influenced by some assignable or special cause variation, and the process performance, as we can obviously see, will not be considered as consistent. So we need to find out the reason for that assignable cost variation, attack the same, and make the process performance consistent before applying the Six Sigma tools and techniques. Clear? But then if you are going to construct run chart using Minitab, we need to refer to a metric called p-value. So more about this metric we will discuss as part of the analyze phase. But for now, understand when we actually construct run chart using Minitab, we will get this metric called p-value. So what is the criteria? If p-value is greater than 0.05, so 0.05 is the standard value. So p-value is greater than 0.05 for all the four non-random characteristics, then the data distribution is considered to be random. On the other hand, if the p-value is less than 0.05 for any of the four non-random characteristics, then the data distribution is said to be non-random due to that specific non-random characteristic. In fact, there will be a question with regard to this in the final assessment. So they would have given p-values for all the four non-random characteristics: trends, oscillation, clustering, and mixture. And they will ask you to infer. So if you find the p-value to be less than 0.05 for any of the four non-random characteristics, then we need to infer that the data distribution is non-random due to that specific non-random characteristic. So if trends alone, has a p-value less than 0.05, so all the other three non-random characteristics have a p-value greater than 0.05, then what will be your inference? You will infer that the data distribution is non-random due to trends. So that will be my inference. So there can be a question on this. So they would have given p-values for all the four non-random characteristics, and they will ask you to infer. So moment you find the p-value to be less than 0.05 for any of the four non-random characteristics, then we need to infer that the data distribution is non-random due to that specific non-random characteristic. Clear? So this is the primary objective of creating a run chart. So we would want to validate whether the data distribution is random or non-random. Only if the data distribution is random, we can infer that the process is influenced by common cause variation alone, and the process performance is also consistent. On the other hand, if the data distribution is non-random due to any of the four non-random characteristics, that is trends, clustering, oscillation, and mixture, then we need to infer that the process is influenced by some assignable or special cause variation, and the process performance is also not stable. And as I told you, we would be able to apply Six Sigma tools and techniques only if the process performance is consistent. That is only when the process is influenced by common cause variation alone. Because in a Six Sigma, as we have already seen, we will be trying to reduce this common cause variation, right? So attacking the assignable cause variation, we will do it as part of the lean project, because when it is assignable cause variation, we will also know the reason behind that assignable cause. But only when it is a common cause variation, we will try to reduce it as part of our Six Sigma initiative. Then what are the 4 rules that we can apply in order to identify the presence of the non-random characteristics in a data distribution? So the first rule, if you observe 6
But I
consecutive
have a
data points,
question here.
yeah.
So, the rules that you mentioned here, so why the number 6, 8, 14 and p-value, the value is 0.05? Like, how
No,
did we get
0.05, we will look at, why it is 0.05 when we discuss more about p-value in the analyze phase, right? So analyze phase will also be covering a concept called testing of hypothesis. So only after you learn, the testing of hypothesis concepts, you'll be able to appreciate this metric called p-value. So the 0.05 will get the answer at that time, right? So just wait for some time. So we'll get into the third phase. We will discuss about this p-value quite extensively. But then 6, 8, and 14, there should be some logic, right? Frankly speaking, I myself do not know what is the technicality behind 6, 8, and 14. There should be definitely some scientific logic. So which might be beyond our scope of learning, right? So I sincerely do not know why it is 6, 8, and 14. I also searched a lot of materials, but I couldn't find any proper explanation why it is 6, 8, and 14.
Okay.
Okay. Just need to go by this. That's it. So 6 consecutive data points showing an upward or downward. There should be some formula. They would have used some technicalities to arrive at these values. So someone would have done some research, right, in order to arrive at 6, 8, and 14. But then it is beyond our scope of learning. So I also kind of, try to find out, because people do ask me every now and then why it is 6, 8, and 14. So I also try to, find out whether there is any explanation for this. But unfortunately, nothing is mentioned about this, right? So no explanation is given as to why it is 6, 8, and 14. So I myself, even my professor doesn't know why it is 6, 8, and 14. That is the truth, right? So anyway, we will just consider this as 6, 8, and 14. So 4 rules that we can apply. So 6 consecutive data points showing an upward or downward trend. So we would call that as non-randomness due to trends. And then 8 consecutive data points clustered on one side of the average line. We would call that as non-randomness due to clustering. But then 14 consecutive data points alternating up and down the average line, we would call that as non-randomness due to oscillation. And finally, if you have 2 sets of data points getting plotted at 2 different levels in a run chart, we would call that as non-randomness due to mixture. But then in Minitab, you will also get to see a metric called p-value. And the criteria here is if p-value is greater than 0.05 for all the 4 non-random characteristics, then the data distribution is random. If the p-value is less than 0.05 for any of the 4 non-random characteristics, then the data distribution is considered to be non-random due to that specific non-random characteristic. So why this 0.05 as the criteria is applied for this p-value? We will definitely learn about it when we actually discuss a concept called testing of hypothesis as part of the analyze phase, where there are certain things which you would learn as part of the discussion. Only then you'll be able to appreciate why it is 0.05. So there's something called confidence level, margin of error, etc., which we will learn right in deep when we cover this testing of hypothesis. At that time, you'll also be able to understand why it is 0.05. Fine. So we look at an exercise and then we'll try to construct a run chart using Minitab. First, we will visually observe and then find out if there is any non-randomness in the data distribution. And then we'll also kind of validate our inference with the p-value output. So let me just click on the next sheet titled Run Chart and RTY. So we have been provided with hour-wise production data in kilograms for some 30 hours, right? And we have been asked to construct a run chart and make necessary inference. So since we are going to construct run chart using Minitab, So I will just copy paste this entire table. So wherever I have not provided any template, you can very well understand those exercises will not come as a question in the final assessment. So in fact, 50% of the exercises that we are going to solve, right, may not really come as a question in the final assessment. But then these are very, very important for you to understand as a black belt. So that is why I'm kind of solving all these exercises. So for constructing the run chart in Minitab, we just need to copy paste the entire table in the Minitab worksheet. And then we need to go to Stat, Quality Tools. Under Quality Tools, we have Run Chart. So we have the data arranged in a single column, which is production in kilograms, and the subgroup size is the hour reference. And we will say plot subgroup medians. So only if the data set doesn't contain any outlier, we can say plot subgroup means. But if the data set contains any outlier, we need to choose the option plot subgroup medians. So we don't want to take a chance. So this data set may contain outlier value. So anyway, to be on the safer side, I'm choosing plot subgroup medians, and then we click OK. So I get to see the run chart. So what are all the things that we can infer immediately applying those 4 visual rules? So one thing is we can see a downward trend of data points, right? It should be more than 6 consecutive data points showing a downward trend. So obviously it is non-randomness due to trend. And we could also observe 8 consecutive data points clustered below the average line. So this is the median line, right? The horizontal line is the median line. And we could find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 consecutive data points clustered below the average line. So even if you have 8 consecutive data points clustered below the average line, we need to infer that the non-randomness is due to clustering. But then we don't find any oscillation. So we don't find 14 consecutive data points alternating up and down the average line, nor do we find any mixture, right? We don't find 2 sets of data points getting plotted at 2 different levels in this run chart. So oscillation and mixture are absent, but we can definitely see non-randomness due to trends and clustering, right? So visually, I've just applied those 4 rules, and I have come up with the inference that this data distribution is non-random due to trends and clustering. But if you are going to look at this box below, so you'll also see the p-values for all the 4 non-random characteristics. So p-value for clustering, it is 0.001 less than 0.05. P-value for trends is 0.00005, again less than 0.05. So non-randomness due to clustering and trends. But then if look at p-value for mixture, it is 0.998, which is greater than 0.05. And p-value for oscillation, it is 0.999, which is again greater than 0.05. So looking at the p-value also, we can infer that the data distribution is non-random due to trends and clustering. So let me just copy paste this run chart in the exercise file and provide the inference. So let me provide the visual inference as well as the p-value inference. First, the visual inference. So we could observe more than 6 consecutive data points showing a downward trend and more than 8 consecutive data points clustered on one side of the average line, clustered below the average line. So there is no indication of oscillation and mixture. Hence, the above data distribution is non-random due to trends and clustering. Right? So this is the inference after visually observing the run chart. Now the p-value inference. So the p-values for trends and clustering are less than 0.05, whereas for oscillation and mixture, it is greater than 0.05. Hence, the data distribution is non-random due to trends and clustering. But then, as I told you in the final assessment, they would have given p-values for all the 4 non-random characteristics, and they will ask you to infer. So if you find the p-value for any of the 4 non-random characteristic to be less than 0.05, we need to infer that the data distribution is non-random due to that specific non-random characteristic. So this is how we will construct the run chart and provide the inference. So go back to the notes file, and the next one, that is the final graphical format that we are going to look at, is box whisker plot. Now, what is this box whisker plot? So we have discussed about the outliers or extreme values in the data set which can occur due to the presence of assignable cause variation, right? But then how to identify that a particular data set contains some outlier value, right? So since we had only 5 data points, so we could identify 50 as an outlier value. And 50 is distinctly different from the other data points, so we can easily identify that as an outlier value. But then if you have hundreds of data points in the data set, which would be the case in a practical scenario. So how can you identify whether there is presence of outliers or extreme values in the data set? We need to use box whisker plot. Another thing here is when we have the data set as 1, 2, 3, 4, 5, we can easily infer that 50 is an outlier value. But then if you have the data set as 1, 2, 3, 4, 5, and then suddenly you have a value 8, whether that 8 can be treated as an outlier or extreme value will be a question mark. We cannot definitely say, right? And for that, we need to definitely use this box whisker plot to find out whether 8 in the data set containing the values 1, 2, 3, 4, 5 can be considered as an outlier value or not, right? And also when you have the voluminous data, and if you want to identify the presence of outliers in the data set, then we need to use obviously the box whisker plot for the same. So this is the tool which would help us to identify the presence of extreme values or outliers in a data set. And the box whisker plot will look something like this. So we will have the horizontal scale at the top. This horizontal scale will have the data set arranged in an ascending order flowing from left to right, meaning the least value or the minimum value in the data set will be to the left extreme, and the maximum value in the data set will be to the right extreme. So we will have a horizontal scale. We can also have a vertical scale, but horizontal scale, it will be easy for you to understand. So that is why I'm drawing this horizontal scale. So this horizontal scale will have the data set for which we are constructing the box whisker plot with the data points arranged in an ascending order flowing from left to right, right? And the box whisker plot can be constructed below this horizontal scale, and it will contain a rectangle box at the center with 2 whiskers extending on either side of the rectangle box. So the box whisker plot will contain a rectangle box at the center with 2 whiskers extending on either side of the rectangle box. So the entire box whisker plot will be segregated in terms of quartiles. So the left-hand tip of the whisker is nothing but the horizontal line that is protruding from the rectangle box. So the left-hand tip of the whisker will be Q0 and the left-hand tip of the rectangle box will be Q1 and the center of the rectangle box will be Q2 and the right-hand tip of the rectangle box will be Q3 and the right-hand tip of the whisker will be Q4. So the entire box whisker plot, as we can see, will be segregated in terms of quartiles. So the left-hand tip of the box whisker or the left-hand tip of the whisker will be Q0. This Q0 is the outlier limit on the lower side. So Q0 is the outlier limit on the lower side. And the right-hand tip or the left-hand tip of the rectangle box will be Q1. So Q1 is called as the first quartile or the 25th percentile. So you'll understand what exactly is 25th percentile. And the center of the box will be Q2, which is the second quartile or the 50th percentile. And the right-hand tip of the box will be Q3. So the right-hand tip of the rectangle box will be Q3. So Q3 will be the third quartile or the 75th percentile. And the right-hand tip of the whisker will be Q4, which will be the outlier limit, the upper side. So Q0 is the outlier limit on the lower side and Q4 is the outlier limit on the upper side. Right? So when I say quartiles, it means that the consecutive quartile points will be separated by a distance of 25% of the data points in the data set, meaning the first 25% of the data points in the data set will lie between Q0 and Q1. And the next 25% of the data points in the data set will lie between Q1 and Q2. The third 25% of the data points in the data set will lie between Q2 and Q3. And the final 25% of the data points in the data set will lie between Q3 and Q4. So that is why it is called as quartile. That means any two consecutive quartile points will be separated by a distance of 25% of the data points in the data set. So this is how it will be separated. Now, we are talking about Q1, Q2 and Q3 as the quartile values, but then Q0 and Q4 are the outlier limits on the lower side, which you'll see slightly later. Now, what is Q1? It is written as first quartile or 25th percentile. So what do you mean by 25th percentile? Say, for example, you have 100 data points arranged in an ascending order. So the value lying in the 25th position will be the Q1 value. So I am considering 100 data points for calculation convenience, nothing else. We can have any number of data points in the data set. But then if you have 100 data points arranged in an ascending order, then Q1 will be the value lying in the 25th position. Similarly, Q2 will be the second quartile or the 50th percentile. So what is this value? Again, if you have 100 values arranged in an ascending order, then the value lying in the 50th position will be Q2. And 50th position will be the central value, right? When you arrange the data set in an ascending order, the value lying in the 50th position will be your central value, right? So what is the central value called as? It is referred as median. So Q2 will be your median value, right? And then Q3 will be the third quartile or the 75th percentile. Again, when we arrange 100 data points in a ascending order, the value lying in the 75th position will be my Q3 value. So Q1, Q2, and Q3, all these three quartile points can be ascertained from the data set. But Q0 and Q4, the outlier limit values are something that we need to calculate applying a formula, right? So Q1, Q2, and Q3 can be obtained from the data set, right? The 25th percentile, 50th percentile, and 75th percentile. Whereas Q0 and Q4, the outlier limit values need to be calculated by applying a formula. And for that, we are going to calculate a metric called IQR. IQR, the full form is interquartile range. And IQR represents the length of the rectangle box in a box whisker plot. So this is interquartile range. And this is nothing but the length of the box whisker, that is the length of the rectangle box in a box whisker plot. And how will you calculate IQR? So this will be Q3 minus Q1. So Q3 minus Q1 will give you the length of the rectangle box. So IQR will be Q3 minus Q1. So with this IQR value, we can calculate Q0 and Q4. So Q0, as I told you, is the outlier limit on the lower side. So Q0 will be, so as we can see in this box whisker plot, Q0 will be a value less than Q1. So when we have the data points arranged in an ascending order flowing from left to right, so we can clearly understand that Q0 will be a value less than Q1. So Q0 will be Q1 minus 1.5 into IQR. Again, this 1.5 is a constant value, right? It's a constant value. It is considered as arm's length. One arm's length is 1.5. So 1.5 is a constant value, right? So Q4 will be a value greater than Q3. So when we have the data set arranged in an ascending order flowing from left to right, so Q4 will be a value greater than Q3. So Q4 will be Q3 plus 1.5 into IQR. So Q4 will be Q3 plus 1.5 into IQR. So Q0 will be the outlier limit on the lower side. Q4 will be the outlier limit on the upper side. So when we calculate these two values, Q0 and Q4, and if you observe any data point in the data set which is less than Q0 or greater than Q4, then those data points will be treated as outliers or extreme values. Clear? So this is how we would calculate and then kind of find out whether the data set contains any outlier or extreme value, right? But then you can straight away construct the box whisker plot in Excel or in Minitab and find out if the data set contains any outlier value or extreme value. But the manual calculation can be done like this. So Q0 will be the outlier limit on the lower side. Q4 will be the outlier limit on the upper side. So once we obtain the Q0 and Q4 values by using this formula, then we need to find out if there is any data point in the data set which is less than Q0 or greater than Q4, then those data points will be termed as outliers or extreme values in the data set. And this is the explanation I have given here. So box whisker plot, as I told you, is the tool which would help us to identify the presence of extreme values or outliers in a data set. So we will have a horizontal scale containing the data set with the values flowing from left to right in an ascending order. And the box whisker plot will contain a rectangle box at the center with two whiskers, the horizontal lines, extending on either side of the rectangle box. So the entire box whisker plot will be segregated in terms of quartiles. That means the distance between any two consecutive quartile points will be 25% of the data points in the data set. So the left extreme of the whisker will be Q0, which is the outlier limit on the lower side. The left-hand tip of the rectangle box will be Q1, which is the first quartile or the 25th percentile, which means if there are 100 data points arranged in an ascending order, the value lying in the 25th position will be Q1. And the center of the rectangle box will be Q2, which is second quartile or 50th percentile. Again, if you have 100 data points arranged in an ascending order, the value lying in the 50th position will be Q2, and that central value is what we would call as median. And the right hand tip of the rectangle box will be Q3, which will be the third quartile or the 75th percentile. Again, if you have 100 data points arranged in an ascending order, the value lying in the 75th position will be Q3. And then Q4 will be the right hand tip of the whisker. So Q4 is the outlier limit on the upper side. So while Q1, Q2, and Q3 values can be ascertained from the data set, we need to calculate Q0 and Q4 by applying a formula. So for this, we need to first obtain a metric called IQR, which is interquartile range, and we can use the formula Q3 minus Q1, which would indicate the length of the rectangle box in a box whisker plot. And with this IQR value, we can calculate Q0 and Q4. So Q0 will be Q1 minus 1.5 into IQR. Q4 will be Q3 plus 1.5 into IQR. So if you find any data point in the data set which is less than Q0 or greater than Q4, then those data points will be considered as outliers or extreme values, right? So what we are going to do, we are going to look at how to perform this box whisker plot calculations for this processing time data set. We already know that this processing time data set doesn't contain any outlier or extreme value, right? Because the mean and median have the same value, right? So that means there are nil outliers in this data set. But still, let us see how to perform the calculations using the Excel and manual formula, and then come up with the final inference that there are nil outliers in this data set, right? So I'll provide the title box whisker plot calculations. So we will see the calculations first, and then we will also see how to construct histogram and box whisker plot for this processing time data set. So I'll give the title box whisker plot calculations, right? So first let me calculate the Q1 value, which is the first quartile or 25th percentile. Right? So you can apply the Excel formula to perform the calculation. Otherwise, what you need to do? We need to first arrange the data set in an ascending order. And then we need to calculate what is 25% of 30, because we have only 30 data points here. So we need to calculate 25% of 30. We will get the answer as 7.5, which has to be rounded off to the nearest whole number, say 8. So the value lying in the 8th position after you arrange the data set in an ascending order will be the Q1 value. So like this, we need to identify Q2 and Q3 values. Instead, we can straight away apply the Excel formula. So when we apply the Excel formula, as I told you, we don't have to arrange the data set in an ascending order, right? So that is the advantage. So straight away, let me apply the Excel formula for quartile. So the formula is equal to quartile.exe. Again, I repeat, no need to worry about all these formulas, no need to by heart any of these things. So is equal to quartile.exe. Array means we need to provide the range of the data set. So the range of the processing time data set, comma, without leaving any gap, we are finding out the first quartile, so provide the value 1. So moment you provide the value 1, the Excel will understand you are trying to calculate the first quartile value. Close the bracket, enter. So 5.1 is the Q1 value. So I will also write the Excel formula by the side. So is equal to quartile.exe, provide the range of the data set, comma 1. Right. Next we will find Q2, which is the second quartile or the 50th percentile. So again apply the formula is equal to quartile.exe, and this is what we will call as median. So we already used the conventional formula to get the median value, which is 5.2. Let us see. Applying the quartile formula also, we get the same 5.2 as the value. So quartile.exe, and then we need to provide the range of the data set, comma 2 will give you Q2. So Q2, applying the quartile formula also, we get the same value, 5.2. So this will be is equal to quartile.exe, range of the data set, comma 2. And this is what we will call as median. And then Q3, which will be third quartile or 75th percentile. Right? Again, apply the Excel formula is equal to quartile.exe, open bracket, provide the range of the data set, comma 3. So 5.3 is the third quartile. So is equal to quartile.exe, and then the range of the data set, comma 3, the third quartile, right? Now I need to find out IQR. So IQR is the interquartile range. Interquartile range. So this can be obtained by using the formula Q3 minus Q1. So what is Q3? 5.3 minus what is Q1? 5.1. Right? This will be my IQR. So this is Q3 minus Q1. This is a manual formula. Now with this IQR value, I will be able to calculate Q0 and Q4. So Q0, which is the outlier limit on the lower side. So this will be Q1 minus 1.5 to the IQR value. So Q1 minus 1.5 into IQR. Right? And then Q4 will be the outlier limit on the upper side. So this is outlier limit, the upper side, and the formula is Q3 plus 1.5 into IQR, 5.6. Q3 plus 1.5 into IQR, right? So we get the outlier limit values as 4.8 and 5.6. But then, is there any data point less than 4.8 or greater than 5.6 in this data set? Definitely not, right? So because we already, calculated the minimum and the maximum values in this data set, which is ranging from 5 to 5.4. So this, minimum and maximum value range is well within the outlier limit range, right? So you'll not find any value in the data set less than 4.8 or greater than 5.6. So we can infer that this data set doesn't contain any outlier value. So I'll also come up with the final inference, right? Since the minimum and maximum values in the processing time data set are well within the range of the outlier limit values, we can infer that the processing time data set does not contain any outlier value. So this we already inferred by looking at the mean and median value, right? The same inference we are getting for the box whisker plot calculations as well. The same inference is made even after performing the box whisker plot calculations. But then if you are going to straight away, construct the box whisker plot, we can identify whether the data set has any outlier value or not. So we don't even need to perform all these calculations. So we just need to highlight the data set for which we need to, or we want to construct the box whisker plot. So you need to go to insert, and then we have the recommended charts with the subsection containing all these bars. So down below is the box whisker plot. So this is how the box whisker plot will actually look like. So this has been constructed for a vertical scale, right? So here you find there is no presence of outlier. If at all any outlier value was there in the data set, it would have got indicated by a blue color dot. I don't find any blue color dot in this box whisker plot. So which says that this processing time data set doesn't contain any outlier value, right? So I will also purposefully include an outlier value and show you how that value would get indicated in a box whisker plot. So since I know 5.6 is the outlier limit on the upper side of the data spectrum, I will purposefully include a value 5.8, right, which would fall outside the outlier limit on the upper side of the data spectrum. So 5.8 should be identified as an outlier value by the box whisker plot. Let us find out how it gets indicated. So again, we need to highlight the entire data set and then go to insert, the recommended charts, and we see the box whisker plot. Yeah. So you find the blue color dot being displayed here. So keep the cursor on top of the blue color dot. It will help you to understand which value in this data set has been considered as outlier value or the extreme value, right? So instead of performing all these calculations, straight away we can construct the box whisker plot and find out whether the data set contains any outlier value. But then it's important for you to understand how to perform all these calculations. But then if it is slightly heavy for you to really comprehend, no worries at all, right? The next for exercise, we are going to solve using the template, the same box whisker plot calculations. We are going to solve using template because a similar format can come as a question in the final assessment, right? So we can also construct histogram for this data set because processing time, as we all know, is a continuous data. So histogram is the appropriate graphical format for representing continuous data. So we can construct histogram for this processing time data set. So for that, we need to highlight the processing time data column. And we need to again go to insert recommended charts, one with all these bars. The first one itself is histogram. So it won't be a clear representation, right? The Minitab output would be much better than this, but then we get to see something. So this is how we will construct histogram in Excel, right? So let me also kind of construct the histogram and box whisker plot in Minitab. So I've already copy pasted the processing time data set here. So for constructing the graphs, we need to go to, or we need to click on this tab, graph, and then the histogram is right here in the list. Just click on that. So I will say histogram with fit, click OK. So the graph variables, the processing time, column header reference will be given, and we click OK. So you get to see the histogram. right? We see a symmetric bell curve indicating that the data distribution is normal. And you can also construct the box whisker plot. Go to graph and we have box plot here. Click on that. So since we have only one data set containing processing time, so we can choose the simple one and then click on OK. So processing time column header, we need to double click on that. Then we click OK. And you get to see the box whisker plot. So keep the cursor on top of this box whisker plot diagram. So you'll get to see what is the Q1 value, what is the median. Median is the Q2 value. And what is the Q3 value, what is IQR, right? All these important matrices will get displayed here. So Q1 is 5.1, Q2, which is the median value, is 5.2, Q3 is 5.3, IQR, which we calculated, is 0.2. But then if you want to see both these graphs and also the descriptive statistics measures in one single screen, then we need to go to Stat, Basic Statistics, and there is something called Graphical Summary. So Stat, Basic Statistics, and Graphical Summary. So under this variables field, we need to enter the processing time column header and we click OK. So immediately get to see the histogram constructed for the processing time data set along with the box whisker plot down below. And on the right hand side, you can see the descriptive statistics measures. Mean is 5.2, standard deviation 0.1114, variance is 0.0124, skewness is 0 because it is a symmetric bell curve. And the minimum value in this data set is 5. The maximum value is 5.4, which we also calculated. First quartile is Q1, 5.1. Median is Q2, 5.2. Q3 is the third quartile, 5.3. So all these values are matching perfectly with our output as well. Right? So this is how we will get to see the entire graphical summary. So let us see how the outlier value gets represented in Minitab. So let me purposefully include the outlier value 5.8 and see how it gets indicated in Minitab. So we can go to Stat, Basic Statistics, Graphical Summary. So we erase the earlier reference and then double click on the processing time once again. Click OK. So as we can see, because of the single outlier value, the histogram has got totally distorted. So we see a longer tail on the right hand side for the bell curve, meaning that it is positively skewed because the outlier limit or the outlier value is on the upper side of the data spectrum. And if you look at the box whisker plot, the outlier value is indicated by this asterisk mark. So in the Excel output, the outlier value will be indicated by that blue color dot. But here, so the outlier value will be indicated by this asterisk mark. So keep the cursor on top of the asterisk mark. It will let you know which data point and the row reference for that data point, which has been considered as outlier value, will be clearly indicated. And then you see mean has got influenced by this outlier value. So from 5.2, it has gone up to 5.2194. Whereas median, it was earlier 5.2, it remains as 5.2 despite the presence of this outlier value, which is 5.8. And you see standard deviation variance. So all these things have got spiked because of the presence of outlier value. And we see some positive value for skewness. That means it is positively skewed, right? We have the outlier value on the upper side of the data spectrum. So this is how we will create the graphical summary and then construct histogram, box whisker plot, and also look at some of the key descriptive statistics measures. Fine. So this is as far as exercise number 1 is concerned. Now we'll move on to the next exercise. As I told you, a similar format can come as a question in the final assessment. So it's a very simple exercise. We are going to use the template in order to solve this. So we have been asked to identify the outlier limit excluding median. So you don't have to really worry about this term excluding median. So what we need to do is we need to calculate the outlier limit value on the upper side. That means we need to calculate the Q4 value for the data set. So they're given some data points. So in the assessment question also, you will find the data points, provided like this. So what we need to do, so we need to input all these values in this input data column. So we need to arrange this in a vertical structure. So you don't have to arrange this in an ascending order. So we can, retain the same sequence as it is given in the question. But then we need to arrange this in a vertical structure. The only thing that we need to do, just input the data in this column, input data column. So 16, 15, 17, 2, 3, 9, 8, 6, 7, 2, and 5. So we have total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 data points, and we have 11 data points entered in this input data column as well, right? So this, template can accommodate up to 15 data points in the data set. So you'll not get a question with more than 15 data points, right? So this template is more than sufficient. So as we enter all these input values in this input data column, we can see the answers populating in the output section, right? So that's the beauty of this. So Q3 value is 15, Q1 value is 3, IQR is 12. So Q4 is the value that we have been asked to calculate, which is 33. So we need to look at the multiple options given for this question, and we need to pick the value 33 from that list. Of course, you won't get the same data points that you see here. The data points could be different, but it will be in the same format, right? So what is the answer? So Q4 value is what we need to find out, and the answer is 33. We didn't use any formula here. We didn't perform any calculations. Just we have entered the values in this input data column, and we would automatically get the answers populating in the output section. So simple, right? Using the template. So that's why I told you the assessment, the final assessment, even if you are aware of all these formulas, right? Please do not, use these formulas and then perform the calculation. So it will definitely consume a lot of time. So please use the template. Just input the values. You don't even need to arrange the data set in an ascending order. Just input the values in the same sequence. In this input data column, you would automatically get the answers in the output section. Right? So suppose, they are asking you to calculate IQR for a data set. Then you can pick the value from this output section. So all possible metric values is getting displayed in this output section. Fine. So this is exercise number 2. A similar format, as I told you, can come as a question in the final assessment. Now moving on to exercise number 3. So you'll also get a similar question in the final assessment. But then this is not a question which requires calculations to be done, right? So this is not a question which requires calculations to be done. So this is a logical question. So if you are very well aware of the box whisker plot concepts, you should be able to answer this question quite comfortably. So what is this question? It says IQR calculation for the data set containing the marks scored by students in a class is 80 minus 40. So IQR is given as 80 minus 40. So if IQR is given as 80 minus 40, what is Q3 and Q1? So what is Q3 value? So IQR is given as 80 minus 40 means, so what is IQR? IQR is Q3 minus Q1. So it is given as 80 minus 40. That means what is Q3? So Q3 will be 80 and Q1 will be 40. So this is what I can interpret from the first part of the question. Now moving on to the second part. It is asking us to estimate the percentage of students who have scored more than 80 marks. So 80 is the Q3 value. So if you want to estimate the percentage of students who have scored more than 80 marks, that means we need to estimate the percentage of data points beyond that Q3 level in a box whisker plot. So what percentage of data points would lie beyond Q3 in a box whisker plot? Tell me.
25.
So what percent? 25%. That's it. Right? So 25% is the correct answer. Suppose they had asked you to estimate the percentage of students who have scored less than 80 marks, then it will be 75%. Because 80 is the Q3 value, as we can see from that IQR formula. IQR is given as 80 minus 40. So we can understand that Q3 is 80. So we have been asked to estimate the percentage of students who have scored more than 80 marks. That means we need to estimate the percentage of data points that would lie beyond Q3 in a box whisker plot, and it is 25%. That's it. Right? So 25% is the correct answer. So in a box whisker plot, we will have 25% of the data points which would lie beyond Q3. Hence, or we'll say, since Q3 value is 80, so we will have 25% of the students who would have scored more than 80 marks. So 25% is the value that we need to pick from the multiple choice. So you can get a similar question in the final assessment. So exercise number 3. So exercise number 2, exercise number 3 can come as questions in the final assessment, right? May not be the exact values. Values could be different, but similar format. So we need to apply the same logic. As I told you, for the calculations, we need to apply or we need to use the template, right? So for exercise number 2, we were asked to calculate the outlier limit on the upper side, which is nothing but your Q4 value. So we need to enter the data set in this input data column, the same sequence. You don't have to really arrange the data set in an ascending order. So moment you enter all the values in the input column, just ensure that you don't miss out entering any of the data point in this input data column, right? So that's the only thing. Just count the number of data points that are provided to you in the question. So ensure that all the data points are entered in the input data column. That's it, right? So moment you have entered all the data points in this input data column, you can just look at the answers in the output section and pick the relevant value. Right? So this I told you is a logical question. So you don't require any calculations to be done for exercise number 3. So if you are aware of the box whisker plot logic or box whisker plot concept, you would be able to easily answer this particular question. So IQR is given as 80 minus 40. So which means the Q3 value is 80 and Q1 value is 40. And we have been asked to estimate the percentage of the students who have scored more than 80 marks. So it typically means that we need to estimate the percentage of data points that would lie beyond the Q3 value in a box whisker plot, because Q3 is 80. So only 25% of the data points would lie beyond Q3 in a box whisker plot. So 25% is the correct answer. So let us stop here. So let us continue with our exercise. So tomorrow we will look at exercise number 4, and then we will move on to the next concept in the measure phase, right? So you'll be solving quite a good number of statistical exercises in this measure phase. So better be prepared. So we'll be looking at some advanced tools as well going forward. But then I hope, we have had a good start. So we are going to keep things very, very simple like this, right? You don't have to really worry. So again, I repeat, for all those, statistical exercises that are going to appear as questions in the final assessment. So I have provided you with the template. So you can make use of the template and perform the calculations. So you don't have to really worry about understanding the calculation logic. If you are able to understand, well and good. But even if you are not able to understand, it's absolutely fine. Yes, please.
So, would you be able to explain the logic for Q0 and Q4 in the box whisker plot, like visual representation? How did we derive the formula of Q1 minus 1.5 into IQR? Like, what's the logic behind that?
No. Q1, see, Q0 will be a value less than Q1, right? The box whisker plot, when you have the data points arranged in an ascending order flowing from left to right. So you can see here, Q0 will be a value less than Q1, correct? So that is why we have the formula as Q1 minus 1.5. 1.5 I told you is a constant value, right? Into IQR. IQR is the interquartile range, which is the length of the rectangle box. Whereas Q4 will be a value greater than Q3. Right? When you have the data points arranged in an ascending order flowing from left to right. So obviously Q4 will be a value greater than Q3. So that is why I put Q3 plus 1.5 into IQR.
Got it. Thanks.
Okay. Okay, fine. So let us, close the sessions for the day. So we will continue with our discussions tomorrow as well. So have a good night. We'll connect at the same time tomorrow evening. So thanks for your time today.
Thank you so much.
Thank you. Good
Thank
night.
you.
Thank you, sir.
Thank you.